Preface in Chapter 1 of The Fairy Tales of Science. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Fairy Tales of Science, A Book for Youth, by John Cargill Brough. Preface. To place before the youthful student a compact and concise compendium of the leading and most universally important branches of science has been my principal object in the preparation of this little volume. To adapt the work to the capacity of all, I have endeavoured to divest the different subjects treated in it of hard and dry technicalities, and to clothe them in the more attractive garb of fairy tales, a task by no means easy. That I have been obliged, in the composition of the work, to consult a crowd of authorities need hardly be stated, nor will any more formal enumeration or systematic acknowledgment be expected. In the fanciful sketches which illustrate these pages, my friend, Mr. C. H. Bennett, has most fully entered into the spirit in which I conceived the work. I have to tender my sincere thanks to my esteemed friend Dr. G. L. Strauss, who came to my aid at a time when severe indisposition seemed to threaten that many of these fairy tales of science should remain untold. J.C.B. Stockwell. Chapter 1. The Age of Monsters. Mighty pre-Adamites that walk the earth, of which ours is the wreck. Byron. Once upon a time, if we are to believe our fairy books, a terrible race of monsters devastated this fair earth. Dragons and griffins roamed at large, and a passing visit from one of these rapacious creatures was held to be the greatest calamity that could befall a nation. All the king's horses and all the king's men were powerless in the presence of such a foe, and the bravest monarch stooped to purchase his own safety with the most humiliating concessions. The dragon was allowed to run riot over the face of the country, to devour the flocks and herds at his pleasure, and when sheep and oxen ceased to gratify him, scores of beautiful damsels were sacrificed to allay the cravings of his ravenous appetite. Sometimes the fastidious monster would go as far as to order a princess for dinner, but he generally had to pay dearly for his audacity. When the monarch had exhausted his stock of prayers, and the poor little maiden had almost cried out her eyes, some valiant knight-errant was certain to come forward and challenge the dragon to meet him in the field. A terrific encounter then took place, and strange to say, the knight invariably proved himself to be more than a match for the destroyer, who had hitherto kept whole armies at bay. As instances of this wonderful triumph of right over might, we need only mention that celebrated duel in which the dragon of Wantley was forced to succumb to the prowess of Moore Hall, and that still more famous combat in which the invincible St. George of England won an everlasting renown. We have said that these monsters belong to that mythical age known as Once Upon a Time. Unfortunately, we can find no trace of them in authentic history, and we are compelled to admit that they had their origin in the fanciful brains of those old story-tellers, whose wondrous legends we delight to linger over. In more credulous times, however, these monsters of enchantment were religiously believed in, and no one doubted that they had their lairs in the dark and impenetrable forests, in the desolate mountain passes, and in those vast and gloomy caverns which are even now regarded with superstitious dread by the ignorant. At length the lamp of science was kindled, and its beneficent rays penetrated the darkest recesses of the earth. Roads were cut through the tangled woods, busy factories sprang up in the lonely glens, and curious man even ventured to pry into the secrets of those terrible caves. The monsters of romance were nowhere to be found. Triumphant science had banished them from the realms of fact, with the same pitiless severity that the uncompromising St. Patrick had previously displayed towards the poisonous reptiles of Ireland. The poor ill-used dragon has now no place to lay his scaly head, the griffin has become a denless wanderer, and the fiery serpent has been forced to emigrate to a more genial clime. Fortunately, truth is stranger than fiction. The revelations of modern science transcend the wildest dreams of the old poets, and in exchange for a few shadowy griffins and dragons, we are presented with a whole host of monsters, real and tangible monsters too, who in the early days of the world's history were the monarchs of all they surveyed, and had no troublesome 7 champions to dispute their sway. We are on the shores of the ancient ocean. We search in vain for any sign of man's handiwork. No iron steamship, no vessel of war, no rude canoe even, has yet been launched upon its bosom, though the tides ebb and flow, and the waves chant their eternal hymn, according to those immutable laws which the Creator ordained at the beginning. The ocean teems with life, but it contains no single creature which has its exact likeness in modern seas. Its fishes belong for the most part to the great shark family, but their forms are much more uncouth than those of their savage descendants. No whales, dolphins, nor porpoises are to be found in these waters, their places being filled up by strange marine reptiles, which equal them in bulk and greatly surpass them in voraciousness. Yonder is one of these old monsters of the deep, the Cetiosaurus, or whale-like lizard. As it rests there with its broad back glistening in the sun, it might easily be mistaken for some rocky islet. But see, it moves. Now it lashes the water with its enormous tail, creating quite a whirlpool in its neighbourhood. Now it raises its huge head, and displays a row of teeth at which the bravest might shudder. And now it darts away from the shore, leaving a wide track of foam on the dark blue waters. Another member of the saurian or lizard race is disporting himself in a little bay close by. The imagination of man never called up a shape so weird and fantastic as this, in which we see combined a fish-like body, a long serpentine neck, and a tapering tail of a lizard, the Plesiosaurus. As he paddles through the water with his neck arched over his back in a graceful curve, he looks a very handsome fellow, in spite of the somewhat evil expression of his countenance. But he is anything but handsome, if we judge him by the adage which restricts the use of that epithet to handsome doers. Look at him now, how eagerly he pounces upon every living thing that comes within the range of his pliant neck, how cruelly he crushes the bones of his victims, and how greedily he swallows them. We never witnessed such unhandsome conduct in a monster before. Leaving him at his disgusting banquet, let us now penetrate into the interior of the old continent, where we shall encounter some terrestrial reptiles of a very formidable character, the Dinosaurians, or fearfully great lizards. We are in the heart of a strange, wild country. At our feet runs a mighty river, whose tortuous course we can trace far away on the distant landscape. The scenery around us is grandly picturesque, being diversified by high mountains with harsh and rugged outlines, yawning chasms, swampy plains, and thick forests. Here a broad stream dashes impetuously through a narrow glen, and there a placid lake glistens like polished silver. Huge masses of rock arise in 1,000 fantastic forms on one side, while on the other vast desert tracts, monotonously level, spread out as far as the eye can reach. The general aspect of the country is utterly unlike that of any modern land, and we gaze on the savage panorama before us with mingled feelings of admiration and awe. We are surrounded by wonders. The vegetation which fringes the banks of the river is strangely unfamiliar. Some of the trees remind us of the palms and arborescent ferns of the tropics, and others seem to be allied to the cypress and juniper, but they all belong to unknown species. The air, which is hot and oppressive, swarms with insects. Curious flies and beetles hum around us, and every now and then a huge dragonfly darts past like a meteor. Looking towards the river, other more striking forms of animal life meet our gaze. Hundreds of gigantic crocodiles are swimming in the stream and lying on the muddy shore. Horrible creatures are they, with their thick coats of mail and sharp, elongated muzzles, and we cannot watch their ungainly movements without experiencing an involuntary sensation of disgust. On the oozy banks of the river another type of reptilian life is represented by a shoal of freshwater turtles, which we see crawling along at a slow and steady pace. Now one of these sluggish fellows stops to pick up some dainty morsel, a mussel perhaps, a snail, or a crocodile's egg. But the exertion appears to cost him no small annoyance, and now he draws in his head and prepares for a nap. As he has in all probability 100 years yet to live, he can afford to devote an hour or two to digestion. But hark! What noise was that? Surely that harsh, discordant roar must have proceeded from the deep throat of some monster concealed in yonder forest. The crocodiles seem to understand it perfectly, for see, they are making for the opposite bank with most undignified speed. There it is again, still louder than before. now a crashing among the trees, followed by a wild, unearthly shriek. Look at that terrible form which has just emerged from the thicket. It rushes towards us, trampling down the tall shrubs that impede its progress, as though they were but so many blades of grass. Now it stops as if exhausted, and turns its huge head in the direction of the forest. How shall we describe this monster of the old world, which is so unlike any modern inhabitant of the woods? Its body, which is at least 20 feet long, is upheld by legs of proportional size, and a massive tail which drags upon the ground and forms a fifth pillar of support. Its head is hideously ugly, its immense jaws and flat forehead recalling the features of those grim monsters which figure in our story-books. Its dragon-like appearance is still further increased by a ridge of large triangular bones or spines which extends along its back, the Hylaeosaurus or Wealden lizard. We should not be at all surprised were we to see streams of fire issuing from the mouth of this creature, and we look towards the palm forest, half expecting a St. George to ride forth on his milk-white charger. See, some magical power causes the trees to bend and fall. The dragon slayer is approaching. Gracious powers! It is not St. George, but another dragon, nearly double the size of the first. He proclaims his arrival by a loud roar of defiance, which is unanswered, save by the echoes of the surrounding hills. The first monster tries to conceal himself behind a clump of trees and preserves a discreet silence, being evidently no match for his formidable challenger. The newcomer is certainly a very sinister-looking beast. His magnitude is perfectly astounding. From the muzzle to the tip of his tail he seems to measure about 40 feet, and his legs are at least 2 yards long. His feet are furnished with sharp claws for tearing the flesh from the bones of his victims, and his teeth are fearful instruments of destruction, each tooth being curved and pointed like a sabre, with jagged, saw-like edges. The Megasaurus, or great lizard. His disposition is decidedly unamiable. Look at him now, how furiously he tears up the earth, and how savagely he looks about him for some trace of his lost prey. Now he catches a glimpse of the crested monster among the trees, and dashes toward him with a terrific yell of delight. Alas, there is no escape for you, unfortunate dragon. The great monster can outstrip you in the chase, and you may as well show a bold front. Now they meet in the hollow with a fearful crash. The lesser monster is determined to sell his life dearly, and with the aid of the spines along his back he contrives to inflict some severe wounds upon the huge body of his opponent. What a fearful conflict! How they snort and roar! How they roll over among the ferns, linked together in a terrible embrace! The hero of the crest is the first to rise. He makes off towards the forest, and may yet escape. Alas! He falls exhausted, and the great monster is on his track. His temper does not seem to be improved by his wounds. How angrily he tosses his head, and how fiercely he gnashes his sabre-like teeth. He approaches his fallen enemy. Now he jumps upon him with a crushing force, and now his enormous jaws close upon the neck of his victim, who expires with a shriek of pain. We can gaze no longer at this awful scene. The battle was sufficiently exciting to absorb our attention, but we have no desire to see how the great monster disposes of the body of his valiant foe. Let us therefore leave the river bank and visit another portion of the old continent. We stand in a lovely valley surrounded on all sides by high mountains, whose slopes are covered with luxuriant vegetation. A crystal stream meanders through the fertile plains, and runs into a fairy-like lake, upon whose margin there are little groups of arborescent ferns and palms. The whole valley has the appearance of a rich garden, and we regard its various beauties with rapturous admiration. As we look around, we fail to discover any trace of man. No temple, palace, or hut bears witness to the existence of a being capable of appreciating the charms of which nature has been so prodigal. We are profound egotists, and think that everything beautiful must have been created for our especial advantage. Here, however, trees spring up though there be no woodman to hew them down. Fruits ripen though there be none to gather them, and the stream flows though there be no mill set in motion. In fact, the age of man has not yet dawned upon the earth. We have already seen some of the weird inhabitants of the Old World. This valley is the favourite haunt of another, and a still more remarkable creature, who loves the shelter which these trees afford. Yonder is one of these extraordinary monsters. He has just emerged from the forest, and is marching towards the lake slowly and majestically, a regular moving mountain. His legs are like trunks of trees, and his body, which rivals that of the elephant in bulk, is covered with scales. In length and height he equals the great lizard we have already described, but his whole appearance is far less awe-inspiring. There is a good-humoured expression in his face, and his teeth are not nearly so formidable as those of his predaceous neighbour, being blunt and short, and evidently fitted for the mastication of vegetable food. He is the iguanodon, so named from its teeth, which resemble those of a recent lizard called the iguana. Look, he is quietly grazing on those luxuriant ferns which lie in his path. Now the foliage of a tall palm-like tree seems to offer a tempting mouthful, but it is beyond his reach. There are more ways than one of procuring a meal. See, the huge vegetarian places his forepaws against the stem of the tree and coolly pushes it down. Having stripped the fallen stem of its sword-like leaves, he plunges into the lake and flounders about in the water as though the bath were his greatest source of enjoyment. This huge herbivorous monster would probably be no match for the cruel creature whom we left devouring his enemy by the river, as all its actions prove it to be a harmless and peaceably disposed animal. Look at that strange bird overhead. Its body does not appear to be larger than that of a pigeon, but what enormous wings it is provided with! Now it descends. Is it a bird or a large bat? Its wings seem to be formed of leather, and its body has anything but a bird-like form. See, it alights and runs upon the ground with considerable speed. Now it jumps into the lake and swims about the surface as if water were its natural element. Again it rises in the air, directing its course towards the spot where we are standing, and now it perches upon a fragment of rock close to us. What an extraordinary creature! It is neither bird nor bat, but a winged reptile. Its head, which is small and bird-like, and supported on a long slender neck, is provided with elongated jaws, in which are set some 50 or 60 sharp little teeth. Its wing consists of folds of skin, sustained by the outer finger, enormously lengthened, the other fingers being short and armed with powerful claws. Its body is covered with scales instead of feathers, and in addition to this strange mixture of bird-like and reptilian features, the creature is provided with the long, stiff tail of a mammal. He is the pterodactyl, or wing-fingered lizard. Of all the inhabitants of this country of marvels, the flying reptile is by far the strangest, and as we gaze upon its weird form, we cannot help comparing it with one of those horrible and grotesque imps which are described so minutely in monkish legends. Again the scene changes. The country of the monster fades away, and we are once more in our cosy study, surrounded by our favourite volumes. Perhaps the curious reader would like to know where the marvellous country is situated, but as we do not intend to tack a long scientific essay upon our fairy tale, he must be content with a very few words of explanation. All that remains of the monster's country is a large tract of land or delta which was formed ages and ages ago at the mouth of a mighty river, the Wealden beds, so called from their forming a district known as the Weald of Kent and Sussex. These strata, which were deposited at the mouth of a river rivaling the Mississippi in magnitude, occupy the whole area between the North and South Downs. The continent through which this river flowed now forms a large portion of the bed of the Atlantic. How can we know anything about this submerged country? How can we come to any conclusion respecting the kind of creatures which lived and died there? These questions will probably occur to the reader, and give rise to certain doubts as to the credibility of our narrative. The monsters have been their own historians. They have described themselves in the gorgeously illuminated volume called the Stone Book, every page of which is formed of the solid rock. The truth of the matter is simply this. When the geologist came to examine the structure of the old river delta, he found embedded in the rocks broken and water-worn bones, detached teeth, freshwater shells, fragments of trees, and even the bodies of insects. With untiring industry and perseverance he classified these organic remains. He placed together the gigantic bones, and reproduced the forms of those enormous creatures which are now represented by our tiny frogs and lizards. He examined every leaf and fir cone, and found out the order of plants to which they belonged. Every relic he submitted to close scrutiny, and at length he was rewarded by a vision of the ancient continent and its inhabitants as they existed at that remote period which we can only vaguely describe as once upon a time. End of chapter 1. Chapter 2 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. The Amber Spirit. Puck. I go, look how I go, swifter than arrow from the Tartar's bow. Midsummer Night's Dream. That merry wanderer of the night, Puck, who boasted that he could put a girdle round the earth in 40 minutes, was a sluggard compared with the fairy messenger who now flies hither and thither at our bidding with a velocity which might carry him round the globe several times in a single second. 24 centuries have elapsed since Thales of Miletus evoked this nimble spirit by rubbing a piece of yellow amber, just as the heroes of romance summoned genii, fairies, and hobgoblins by the friction of rings and amulets. The Greek name for amber was electron, and thus our spirit came to be called electricity. The ancients were ignorant of the potency of this ethereal being. Indeed, their knowledge was confined to the isolated fact that amber, when rubbed, acquired the property of attracting light bodies. The grander manifestations of the amber spirit's power received a religious interpretation. Thus, the forked flashes which sometimes darted through the sky were supposed to come from the hand of the mighty thunderer, and those fiery meteors which now and then rested on the javelins of the Roman legionaries were looked upon as omens of victory sent by the war god. It was left for modern philosophers to trace these great phenomena to the amber spirit, and to show that his presence may be detected, not only in the fossil gum which Thales imagined to be his favourite haunt, but in every particle of dust and every drop of water. Let us now describe the cunning means which man employed to enslave this wild spirit. 200 years ago the fragments of amber were laid aside, and a large globe of sulphur was set whirling on a vertical axis, whilst it was rubbed by the hand. By this machine the spirit was dragged from his hiding place, and made to reveal some important secrets. Flashes of light issued from this revolving globe, and balls of pith, feathers, and straw danced toward it as though endowed with life. 60 years later the discovery was made that all solid bodies may be divided into 2 great classes, namely, those which, when held in the hand and rubbed, set free the amber spirit, and those which, under similar circumstances, failed to exhibit any attractive force. Amber, sulphur, and glass belong to the first class, all the metals to the second. It was also found that certain bodies allowed the spirit to pass along them with great celerity, while others completely obstructed his passage. Towards the middle of the last century, cylinders, spheres, and plates of glass were substituted for the cumbrous globe of sulphur, and with these new implements man began to forge the chains which were to bind the subtle spirit. In the year 1746 an ingenious Dutchman actually managed to coax him into a glass bottle, coated within and without with metal, the Leyden jar. But the spirit soon escaped from his narrow prison by passing through the limbs and body of the experimentalist, who received such a violent shock that he was compelled to take to his bed. This incident, however, did not deter the philosopher from prosecuting his inquiries, and his endeavours to construct a secure prison were eventually crowned with success. 6 years after this, an American sage summoned the now docile spirit from the clouds during a thunderstorm by means of a boy's kite, and thus proved the identity of lightning and that force which for 2000 years was regarded as an emanation peculiar to rubbed amber. The 19th century was heralded in by the announcement of a still greater fact. A learned Italian now found that he could dispense with all the old machinery of incantation and evoke the amber spirit by the action of acids upon metals. He piled up alternate discs of zinc and copper, kept separate by the interposition of moistened pasteboard, and with this simple apparatus, the voltaic pile, he obtained absolute control over the movements of the spirit. He compelled him to travel along metal wires of any length, to force asunder the elementary atoms of water, to bring to light substances hitherto unknown, and to perform 100 other feats equally wonderful. The spirit was vanquished, the lightning was chained, and man reigned supreme. It had long been suspected that the magnet owed its peculiar properties to the amber spirit, but the occult relation that subsisted between them had never been detected. This mystery was now cleared up by a Danish philosopher. He caused the spirit to travel along a wire from south to north, and beneath this wire he placed a compass needle. The spirit passed, and lo! the magic needle moved, and assumed a position at right angles with the wire. It no longer pointed to the north, but obeyed the peremptory mandates of the potent spirit. New facts were soon brought to light. Thus it was shown that the spirit could render iron magnetic. A copper wire was coiled round a bar of soft iron, and our spirit was made to run along the wire. The iron at once became a powerful magnet, and exhibited all the properties of the lodestone. These discoveries enabled man to employ the amber spirit as a courier, a vocation for which he is eminently suited, as the speed at which he travels has been estimated at 288,000 miles in a second. Let us see how our messages may be conveyed. In London we have a pile of zinc and copper discs, or what amounts to the same thing, an arrangement of metal plates and acids which we call a battery. We have only to connect the extremities of this machine by means of a wire to set the amber spirit in motion, and he will continue to move as long as the connection remains complete, but will stop the instant it is broken. His route is from the zinc to the copper through the acid solution, and along the wire back again to the zinc. He will never leave the battery at one end unless he is quite satisfied that he can re-enter it at the other, but while there is nothing to obstruct his course, he will continue to circulate through the arrangement without exhibiting the least sign of fatigue. Let the wire which connects the opposite ends of the battery be long enough to reach to Edinburgh and back, and at the northern capital let there be a mariner's compass placed so that the needle shall be directly below and parallel to the wire. It is evident that with this simple apparatus we can compel our courier to travel to Scotland and back. Every time we connect the homeward wire with the zinc end of the battery, the spirit will rush to Edinburgh and cause the magic needle stationed there to move. The deflections of this needle may be converted into intelligible signs. They can be made to spell words. Thus one movement may stand for A, 2 for B, 3 for C, and so on to the end of the alphabet. We have said that our courier will refuse to leave the battery unless he be provided with a return ticket, or, in other words, unless he can secure a safe passage home. It does not follow, however, that his homeward path must be a wire, as by a peculiar arrangement we can force him to find his way from Edinburgh to London through the earth. We have supposed that only one kind of motion can be given to the magnetic needle, and that the amber spirit can only be made to travel in one direction, that is to say, from the copper end of the battery through the wire and back again through the earth. If we connect the wire with the zinc end, this direction is reversed, and as a matter of course, the spirit passes over the needle from north to south, instead of from south to north as before. This new direction is at once detected by the needle, and its north pole moves to the right, whereas it had previously moved to the left. We may take advantage of this double movement in simplifying our alphabet. Thus, one movement to the right may stand for A, one to the left for B, one right and one left for C, and so forth. We will not trouble our reader with any more explanations, but will confine ourselves to consideration of some of the ingenious methods which have been devised to render the amber spirit a useful messenger. Some 20 years ago, a native of this country proposed a system of 5 wires, in connection with as many needles, which indicated the letters of the alphabet at a rate of 20 a minute. Attention was to be drawn to the signals by the stroke of a bell, the hammer of which was moved by the magnetic force which the spirit communicated to a piece of iron. Thus the ear as well as the eye was to be addressed. He afterwards simplified this instrument by employing only 2 wires, and so increased its power that 30 letters could be indicated in a minute. This was known as Wheatstone's telegraphs. In America, another philosopher was simultaneously engaged in perfecting a still more extraordinary contrivance, by means of which the spirit was made to jot down an alphabet of dots and strokes which represented definite characters. The marks were written on a strip of chemically prepared paper, which was made to pass under a fine steel point. This was Morse's telegraph. The spirit had no sooner been taught to write than man set about teaching him the art of printing. Behold him now, a master of the art, printing messages letter by letter in the ordinary Roman characters, under the direction of an operator stationed at a distant city. Bain's printing telegraph. The spirit's education was not yet considered to be complete. He had to acquire another accomplishment. He could communicate intelligence by means of moving needles and revolving dials, by written dots and printed characters, but he could not yet imitate the handwriting of the individual who forwarded the message. An ingenious gentleman now took him in hand, and soon made him an expert copyist. We can now write a letter, have it copied at a remote town in a minute or less, and receive a reply in our correspondent's handwriting, almost as soon as the ink is dry with which it was penned. The Bakewell's copying telegraph. The philosopher Thales wondered to see certain minute bodies fly towards a piece of amber, but how great would have been his astonishment had some superior intelligence informed him that the invisible being which moved the particles would one day be taught to trace figures upon paper exactly like those just written by someone far away. We will not attempt to explain the action of the spirit's magic copying press, as it would lead us too far into the dark domain of chemistry. 100 systems of communication might be enumerated in addition to those we have noticed, so great has been the intellectual activity of the last 20 years. In England, America, and many continental countries, iron wires, plated with zinc to prevent rusting, form the roads along which our ethereal courier travels. These wires are supported by wooden posts, erected some 60 yards apart on every railway. They are not permitted to touch the wood, but are passed through short tubes of porcelain attached to the posts. Were we to omit these little tubes, the spirit would shirk his duty, and would travel no further than the first post, down which he would pass to the earth. These aerial roads are sometimes rendered impassable by fogs, snowstorms, and heavy rains. They are, moreover, seriously affected by Amber Spirit himself when he takes the form of lightning. During a thunderstorm everything goes wrong, and the spirit, having escaped from his thraldom, sets man at defiance. He takes possession of the wires and plays 100 antics. The signal bells ring without ceasing, the wires vibrate to and fro, or remain for hours deflected to one side, while the printing machines strike off unmeaning rows of dots and lines, or long sentences of an unknown tongue. In Prussia, Saxony, and Austria, copper wires, covered with gutta percha, and buried at some little depth in the ground, are employed as a means of communication. These subterranean wires are not subject to the influence of thunderstorms, but in other respects they are more troublesome than those suspended in mid-air. The buried wires are greatly affected by the earth's magnetism and other disturbing influences. Moreover, trenches have to be dug for their reception, and they are with difficulty reached when deranged. Thus we see that each kind of road has its peculiar advantages and defects. As gutta percha effectively cuts off all communication between a wire and surrounding conductors, we make use of this marvellous substance to enclose the wires which convey our spirit through the sea. The practicability of these submarine roads was demonstrated in 1849, when a trial was made with 2 miles of covered wire laid in water. Soon after this a cable was constructed which enclosed 4 copper wires covered with gutta percha, and by means of this cable France and England were brought within a speaking distance of each other. The Amber Spirit soon gave proofs of his ability as a continental messenger, and on the 14th of November, 1851, our great morning journal published a dispatch from Paris, dated 7 o'clock the preceding evening. Another cable was now stretched across the Irish Sea, by means of which England was able to exchange civilities with her sister isle. Others followed, and man, emboldened by their success, now began to think of dispatching his obedient courier across the ocean. Europe was covered with a network of wires, and so was America. To unite these 2 great systems of communication would be a feat unparalleled in the annals of science. This wondrous feat has at last been accomplished, and the 2 great continents are now connected by a cable which lies at the bottom of the Atlantic. At man's bidding, the Amber Spirit speeds along this tremendous cable, and having registered a single letter at its further end, finds his way back to the battery through the pathless deep. Again and again he makes this extraordinary circuit, until every letter in his despatch has been registered, so that, in spelling a word of one syllable, he has to perform a series of journeys which together far exceed the length of Puck's famous girdle. The Amber Spirit has had other duties imposed upon him besides those of a courier. He has been taught to measure time with great accuracy, an accomplishment which scarcely seems to harmonize with his astonishing fleetness. Measuring time must be a tedious occupation to one accustomed to annihilate it. Nevertheless, clocks are moved by our versatile spirit, which have neither weights nor springs, and which will go forever without winding. We have seen how needles may be moved and bells rung. Let us now consider how a pendulum may be set in motion. A battery is connected with a pendulum of peculiar construction, its bob being formed of a hollow brass reel on which a long copper wire covered with silk is coiled. In the clock case, on either side are magnets, fixed so that their opposite poles enter the reel. Our readers have already been informed that a magnet freely supported, as in the mariner's compass, will move when the Amber Spirit passes over it. We will now confide to them another secret, namely, that a fixed magnet will give motion to a movable wire along which the spirit is passing. We shall now be able to explain the motion of our magic pendulum. As soon as the spirit is sent along the coil of wire, the pendulum moves towards one side, being attracted by the one magnet and repelled by the other. But by an ingenious contrivance, the connection between the coil and the battery is now broken, and the pendulum falls back by its own weight, again to be pulled aside by the magnets. The pendulum is thus made to oscillate, and so long as there is power enough in the battery to force the spirit through the coil, it will keep swinging, and give motion to a series of wheels acting upon each other which carry round the hands of the clock. This device is known as Bain's electric clock. Other methods have been devised to render the spirit an effective timekeeper, but the simple arrangement we have described may be taken as the type of them all. The great peculiarity of these wonderful clocks is, that they may be connected by wires and made to keep exactly equal time, though separated from each other by hundreds of miles. With a single battery of sufficient power, all the clocks in London might be kept going, and what is still more extraordinary, the London clocks might be made to regulate those of Edinburgh and Dublin, or even those of Paris and New York. The spirit has been employed to move more ponderous things than pendulums. He has been taught to turn a lathe, work a pump, and propel a boat through the water. But as it is much more expensive to evoke the spirit by means of metals and acids than to raise steam from water, he is not likely to supersede steam as a mover of machinery. In the useful arts, the Amber Spirit has long been employed as a worker of metals, and with his assistance we now cast copper medallions, vases, and statues, without making use of a furnace. We gild or silver all kinds of utensils, and cover the most delicate productions of nature with thin films of metal. We will proceed to consider these mysterious operations. When the spirit is made to travel through a solution of copper, silver, or gold, he decomposes it, and deposits the metal, particle by particle, on the wire which conducts him back to the battery. Now, by attaching a suitable model or mould to this wire, we can procure this metallic deposit in any shape, and by substituting any utensil for this mould, we may cover it with a thin film of gold or silver, electrotype. We have not done full justice to our spirit's abilities, as we have omitted to mention the many services he has rendered to the astronomer, the geographer, the chemist, and the physician. We have said enough, however, to give the reader an idea of his versatile powers. We have shown that he can travel with the rapidity of thought across a continent or an ocean, that he can write and print our messages in the most distant places, that he can measure time as it flies, move all kinds of machinery, and melt copper in cold water. We may search through our old fairy tales and romances in vain to find a spirit capable of performing such miracles as these. End of chapter 2. Chapter 3 of the Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. The four elements. Do not our lives consist of the four elements? Twelfth Night. What is the world made of? According to the ancient doctrine of the four elements, all things are formed of fire, air, earth, and water, and the varieties and differences in the properties of bodies depend entirely on the proportion in which these great principles are mingled. While we confine our observations to the external properties of matter, this beautiful doctrine seems incontestable. If we kindle a few dry sticks on a cool hearth, we may remark that while the wood burns there rises smoke or air. The smoke is followed by flame or fire, moisture or water is deposited on the hearth, and ash or earth remains. Everywhere we can detect the presence of the mighty elements. Fire can be set free from innumerable substances. Air penetrates the pores of all bodies, and covers the world like a mantle. Water forms the all-embracing sea, and nourishes every plant and animal, while earth enters into the composition of all solids, and gives form and stability to the universe. Man himself seems to be built of the four elements, and according to the first theoretical system of medicine, health indicates their perfect balance, and disease the preponderance of one of them. Such is the old doctrine of the four elements. Simple and concise enough, but unfortunately false. Modern science has satisfactorily demonstrated the compound nature of fire, air, earth, and water, and they can no longer be regarded as elements. By the term element we understand any kind of matter which up to the present time has never been decomposed into constituents, and which consequently appears to have a simple nature. The true elementary bodies may be compared to the letters of the alphabet, and the diversified compounds which compose the material world to the words which form a language. Let us examine the imaginary elements of the ancients, and see whether they will help us to arrive at the true solution of the problem, what is the world made of? A candle in burning seems to disappear completely, and when the combustion is over, an insignificant trace of ash from the wick is all that remains to the eye. According to the Greek philosophers, tallow contains an ethereal substance called fire, which, being set free, takes the form of flame. The gradual decrease of the candle is therefore accounted for by the dissipation of its chief constituent. Before we can accept this explanation, we must be quite satisfied that fire is a substance. Wherever we perceive light and heat emanating simultaneously from a combustible body, we say there is fire, but we can bring forward no proof of the material existence of this so-called element. We cannot weigh it, measure it, or put it in a bottle, nor can we imagine it existing apart from a burning substance. Fire, after all, may be nothing but a name for certain phenomena of heat and light. These two great forces are intimately connected. Thus, whenever we raise a solid object to a high temperature, it becomes luminous. First it emits a dull red light, which changes as the temperature increases to orange, then to yellow, and finally to white. The flame of a candle is a white-hot cone of volatile matter, which we vaguely term fire. If we can discover the true nature of this cone, we shall be able to define fire with some degree of accuracy. The chemist tells us that nothing can be absolutely destroyed, and that what we call destruction is merely the conversion of a visible body into an invisible one. To reconcile this statement with the gradual disappearance of the burning candle, we are forced to conclude that the tallow is changed into an invisible gas or vapor, and escapes into the air. Now, as no solid can become aeriform without the agency of heat, the question naturally arises, whence comes the heat that vaporizes the tallow? Everybody is familiar with the fact that a considerable amount of heat is evolved when water is poured upon quicklime, a fact which illustrates the great chemical law that no union of two bodies can take place without a change in their temperature. The intense heat emitted by the flame of a candle may be traced to chemical action. If we cover a lighted candle with a glass shade, the flame will soon begin to languish, and in a few minutes it will expire. The flame seems to rob the confined air of a certain virtue, which is essential to its continued existence. This is the true interpretation of the phenomenon. The air contains a wonderful gas called oxygen, which combines with the vaporized tallow, just as water combines with quicklime, and their union is attended by a development of heat. The phenomena presented by a burning candle may now be easily understood. The tallow is melted and sucked up to the top of the wick, where it is boiled and converted into vapor. This vapor combines rapidly with the oxygen of the surrounding atmosphere, and the heat evolved is such as to render the vapor luminous. To bring about the combustion of the candle, it is necessary to apply heat to the wick, but afterwards the heat which is liberated is more than sufficient to sustain the action. We have now arrived at a tolerably clear conception of flame. It is merely a volatile combustible matter heated to whiteness. Fire is simply a convenient word which we make use of to denote the extrication of light and heat during combustion, and the ancient notion that it is one of the primordial constituents of the material world is no longer tenable. Fire is often spoken of as the destroying element, but we must bear in mind that combustion only alters the state of bodies. There is no actual destruction or loss of weight when a body is burned, though the products of combustion may be invisible. If we set fire to a small fragment of phosphorus and cover it with a dry tumbler, dense white fumes will arise, which will condense on the sides of the glass in snow-like flakes. If we collect this white substance and weigh it, we shall find that it is more than twice as heavy as the phosphorus. How is this? The explanation of this apparent anomaly is simple enough. The phosphorus, in burning, combines with the oxygen of the atmosphere to form this white compound, which is known to chemists by the name of phosphoric acid. The weight of the oxygen is therefore added to that of the phosphorus. Some of our readers will doubtless receive this information with astonishment. It seems scarcely credible that a substance having the appearance of snow should be produced by the union of an invisible gas and a yellow wax-like solid. Chemistry is a science of marvels, and this wonderful dissimilitude between a compound body and its constituents is anything but an exceptional case. In fact, it is this change of properties that distinguishes chemical union from mere mechanical mixture. Our tallow candle is composed of two invisible gases and a black solid, and is therefore a much more extraordinary compound than the white phosphoric acid. When a candle is burned, the products of the combustion are invisible gases. These gases can nevertheless be collected by the chemist, and are found to weigh more than the original candle. Coal, coke, wood, and other combustibles, which are employed as fuel, likewise form gaseous compounds with the oxygen of the atmosphere. This is a very significant fact, for were the products of combustion invariably solid, like phosphoric acid, the world would long since have been buried in ashes. We have examined the first of the so-called elements of the ancients, and have proved it to be a manifestation of intense chemical action between two or more bodies. Let us now proceed to consider the nature of air. There exists a certain thing, says a philosopher of the 16th century, which we do not perceive, and in the midst of which is plunged the whole universe of living beings. This thing comes from the stars, and we call it air. Fire, in order that it may burn, requires wood, but it also requires air. The air, then, is the life, for if air be wanting, all living beings would be suffocated and die. In all ages, the atmosphere has been regarded as the great source of life, and long before the famous dogma of the four elements was propounded, a Grecian sage declared that air was the one universal principle from which everything proceeded. We have already alluded to the fact that combustible bodies combine with a certain gas called oxygen, which is contained in the atmosphere. Our readers will not therefore be surprised when we tell them that air is a mixture of dissimilar gases, but they will marvel greatly when we describe the properties of its constituents. If we boil some mercury or quicksilver in a closed glass vessel, in a few hours the metal will undergo a very extraordinary change. It will lose its metallic character entirely, and in place of the glistening fluid we shall find a heap of bright red scales. As these scales weigh more than the original mercury, we may safely conclude that something has been abstracted from the air contained in the vessel. If we now take a lighted match and plunge it into the air that remains, it will be instantly extinguished. It is therefore evident that the abstracted something is oxygen. Let us close the vessel once more and apply to it a strong heat. The red scales are now converted into metallic mercury, and the air regains its property of supporting combustion. This beautiful experiment proves air to be a mixture of oxygen and a certain gas in which no ordinary combustion will burn. This gas has been named azote or nitrogen. Oxygen forms about 1/5 of the atmosphere, and nitrogen nearly the remaining 4/5. To these components must be added about 1/2000th part of a gas called carbonic acid, and traces of another body called ammonia. Though these last two named constituents bear such a small proportion to the others, we shall presently see that they have important duties to perform in the economy of nature. The composition of the atmosphere is everywhere uniform. We may bring down air from the summit of the highest mountain and collect it in the deepest valley, but we shall not be able to detect the slightest variation in its composition. The same uniformity is apparent when we examine the air of the polar regions or that of the tropics, whether we collect it in the densely populated city or in the untrodden forest. This fact seems all the more wonderful when we consider the contaminating influence of the countless exhalations that are continually rising into the atmosphere. The clouds of smoke poured forth by our chimneys, the expired breath of animals, and the gases that proceed from decaying matters, do not perceptibly disturb the equilibrium of the constituents of the atmospheric ocean. We must remember that this aerial ocean is some 45 miles in depth, and that the vapours which arise from the earth are rapidly diffused through its entire extent. The atmosphere exerts a pressure upon the earth's surface equal to about 14½ pounds upon each square inch, and it has been calculated that its entire weight amounts to more than 5,114 billions of tons, a sum which words may express, but which the human mind cannot appreciate. Our readers will gain a clearer conception of this enormous sum when we tell them that it is equivalent to the weight of a solid globe of lead some 60 miles in diameter. We have said that the atmosphere contains an aeriform body called carbonic acid. Let us now see how this fact may be proved. When quicklime is exposed to the air, it gradually loses its caustic properties, and increases in weight. This increase of weight depends on the absorption of carbonic acid from the surrounding atmosphere. We may expel this gas from the altered lime by heat, and collect it in suitable vessels for examination. We find it to be much heavier than ordinary air, so heavy, indeed, that we may pour it from one vessel to another like water. If we plunge a lighted taper in it, the flame will be instantly extinguished, and if we substitute a mouse or any small animal for the taper, the poor creature will be suffocated. This gas is the chief product of combustion. Our candles and fires are continually pouring it forth into the atmosphere. Animals expire it from their lungs, and it is produced in every case of putrefaction and fermentation. Carbonic acid, so fatal to animal life, is essential to the life of plants. Indeed, the existence of the whole vegetable kingdom depends on the presence of this gas in the atmosphere. Carbonic acid is a compound of oxygen and carbon or charcoal, which substance is the principal constituent of all plants. Every green leaf may be compared to a little chemical laboratory, in which the carbonic acid of the air is decomposed, the carbon being retained by the plant, while the pure oxygen is cast forth into the atmosphere. Vegetables absorb the carbon, which is exhaled in combination with oxygen by animals, and the two great divisions of organized beings are thus indissolubly connected by the interchange of substances necessary to their existence. The old fable of the Hamadryads, who presided over the trees of the forest, and who died when the trees were cut down, shadowed forth a deep truth. In the fairy tales of science we read that the lives, not merely of wood nymphs, but of all living creatures, are dependent on trees and herbs. The atmosphere invariably contains a minute portion of ammonia, another compound body, its constituents being nitrogen and a gas called hydrogen. Ammonia is absorbed by water, and it is therefore brought down to the earth by rain, where it forms a valuable manure for plants. Its importance may be conceived when we state that the nutritious qualities of grain and other vegetable substances are mainly derived from the nitrogen contained in this aerial manure. Watery vapour is constantly present in the atmosphere, though we can scarcely call it a constituent of air. Its presence can be easily demonstrated by putting some ice in a tumbler, for when the glass is sufficiently cool, the vapour will be condensed upon its outer surface in the form of dew. We have resolved air into its component gases, and have thus exploded the old notion of air being an element. Our investigations have brought to light certain bodies which may be justly considered elements, namely oxygen, hydrogen, nitrogen, and carbon. These substances have never yet been resolved into constituents, but we do not dogmatically assert that they are absolutely simple in their nature. We call them elements because we cannot prove them to be compounds, though it is not impossible that they may turn out to be such at some future time. That a mixture of 4 dissimilar elements should produce the life-supporting atmosphere is a fact that may well excite our wonder. Who would suspect that the mild and genial air which envelops our planet could be formed of ingredients which separately exhibit such striking peculiarities, and which combine in other proportions to form compounds all more or less fatal to life? An atmosphere of pure oxygen would be too exciting to be compatible with long life in animals, even if we could imagine the existence of life in a blazing world, for not only those substances which are generally spoken of as combustibles, but even the metals, burn with great violence in oxygen. In an atmosphere of nitrogen, animals could not exist at all. Indeed, this gas formerly went by the name of azote, the literal significance of which is fatal to life. 2 volumes of oxygen mixed with 8 of nitrogen form the breath of life, but when these gases are combined in other proportions, they form compounds which have very different properties. One of these compounds is the protoxide of nitrogen, a gas which may be inhaled for a few minutes without danger, but which is incapable of supporting life for any length of time. When breathed, it produces great mental excitement, and occasions a total loss of volition. The person who inhales it performs 100 strange antics. He talks incoherently, laughs wildly, sings, dances, and sometimes fights. He feels that he is lighter than the atmosphere, and sees all things under a new aspect. In old times these extraordinary effects would probably have been ascribed to some mischievous demon contained in the laughing gas, and the bell, book, and candle would have been deemed indispensable for its exorcism. Another compound is a colourless and invisible gas so poisonous that animals plunged into it instantly expire. A third, a corrosive orange-coloured vapour, equally noxious. And a fourth, the well-known liquid called aquafortis, a powerful acid which dissolves copper and other metals, and which destroys all organic substances. Such are the compounds of nitrogen and oxygen, the very elements which we draw into our lungs at every inspiration, and without which we could not exist. Carbonic acid gas, though incapable of supporting life, is not poisonous, and its presence in the atmosphere does not disturb our vital functions. Animals may be drowned in pure carbonic acid, but they cannot be poisoned by it. If the atmosphere contained another compound of carbon and oxygen, namely carbonic oxide, in place of this innocuous gas, the world would be a lifeless desert, as carbonic oxide is an active poison, and a very small quantity of it would suffice to infect the air. The philosopher who declared that air came from the stars, figuratively expressed a great truth. We have only to examine the wondrous constitution of the gaseous mixture to be convinced that it must have had a celestial origin, and that the potent elements of which it is composed must have been mingled by an all-wise and beneficent power. We have resolved fire into the phenomena of light and heat, and have separated the constituents of air. Let us now summon water into our presence, and compel that supposed element to reveal its true nature. Water, like air, was once regarded as the origin of all things. Indeed, this belief in the universality of moisture may be said to have laid the foundation of speculative philosophy among the Greeks. Water exists in 3 physical states, the solid, liquid, and aeriform. By adding heat to liquid water, we convert it to aeriform water, or steam. By abstracting heat from it, we change it into solid water, or ice. In either case, the chemical composition of water remains unaltered. We can demonstrate the compound nature of water by analysis or by synthesis. In plainer language, by resolving it into its elements, or by forming it from its elements. Let us first see how its analysis may be effected. Some chemical compounds, the red mercurial scales, for example, are decomposable by heat, but water is merely vaporized by this potent agent. To overcome the attractive force or affinity which binds the elements of water together, we must call in the aid of some substance which has a superlative affinity for one of these elements. Such a substance is potassium, the lightest of our metals. When exposed to the air, potassium rapidly loses its metallic character by combining with oxygen, with which gas it forms potash, and we therefore conclude that potassium has a strong affinity for oxygen. If we throw a small fragment of this metal into water, it takes fire and burns, while swimming about on the surface of the liquid, with a brilliant light of a violet-red color. When the combustion is over, no vestige of the potassium remains, but we find that the water has acquired the acrid taste of potash. The chemist thus interprets the phenomenon. Water is a compound of oxygen and a highly inflammable gas called hydrogen. When potassium is thrown into water, it combines with a portion of its oxygen to form potash, and the heat which attends their union sets fire to the liberated hydrogen. It is not the metal that burns so furiously, but one of the constituents of water. Here is a revelation far more wonderful than anything we find in our old storybooks. Oxygen gas is the great supporter of combustion. Even the metals will burn away in it like tinder. Hydrogen is the lightest gas known. It is very inflammable, and gives out an intense heat while burning. Water, the great antagonist of fire, is built up of these two fiery elements. Wherever we find water, we may be sure that these two elements are present. We may detect them in the water of the boundless ocean, the placid lake, and the murmuring rivulet, in the floating cloud and the jagged iceberg, in the raindrop, the hailstone, and the snowflake, in the jewel that glitters upon the bosom of the rose, and in the tear that falls from the mourner's eye. Potassium is not the only substance that decomposes water. Everybody is familiar with the fact that iron rusts when placed in water. Now the rusting of iron is a similar phenomenon to the conversion of potassium into potash. They both depend upon the absorption of oxygen. At a red heat, iron decomposes water very rapidly. When steam is made to pass through a long red-hot iron tube, it is resolved into its elements. The oxygen unites with the iron to form rust, and the hydrogen is set free. By weighing the tube before and after the operation, the chemist is able to determine the proportion in which the two elements are combined. In 100 parts by weight of water, he invariably finds 89 of oxygen and 11 of hydrogen. We may employ our old friend the amber spirit to separate the elements of water, as this versatile being is a most skilful analytical chemist. The spirit can set free the oxygen and hydrogen in two distinct streams of bubbles, whereas the human operator can only liberate one of these gases by forcing the other to combine with some new body. We have spoken of the inflammable nature of hydrogen, but we have not yet explained the phenomena which attend its combustion. This gas, when pure, burns with a very pale flame, the product of its combustion being water, which escapes into the atmosphere in the form of an invisible vapour. If a cool tumbler be inverted over the flame, this vapour will be condensed into minute drops, which will trickle down the inner surface of the glass. The combustion of hydrogen is therefore a manifestation of the intense affinity of this gas for the oxygen of the air. If we mix the two gases in the proportion in which they combine to form water, and apply a lighted match to the mixture, the gases will instantly unite with a deafening explosion. All the water produced will merely suffice to damp the surface of the vessel in which the explosion takes place, as no less than 2,550 measures of the gaseous mixture are required to form 1 measure of water. Here is another marvellous revelation. The two gases have separately resisted every attempt made by the joint efforts of cold and pressure to liquefy them, yet they combine and form water, the type of liquidity. According to the dogma of the 4 elements, everything that is neither fire, air, nor water is necessarily earth. Now a moment's consideration will convince us that innumerable bodies having the most diverse properties are comprised in this definition of the so-called element. We cannot therefore deal with earth as we have dealt with its mighty brethren. We cannot deduce any general conclusions as to its nature from the analysis of a single sample. We may resolve a particular handful of soil into its elements, but we dare not assert that these elements are common to the multitudinous handfuls which constitute the solid portions of our planet. How then are we to proceed with our investigations? Were we to examine in regular order the various compounds included in the ancient conception of Earth, our fairy tale would assume the character and proportions of an encyclopedia. To preclude such a result, we must abandon the analytical method of inquiry, and be content to accept certain comprehensive truths that chemistry has revealed regarding the constitution of different kinds of earth. The diversified compounds which form the material world have been resolved by the chemist into 63 elementary bodies, 50 of which are metals. These elements are rarely found in a state of purity, owing to their strong tendency to combine with each other. The principal ingredients of earth are compounds of oxygen with certain elementary bodies that are never found pure in nature. Silica, the most widely diffused compound, contains oxygen and another of the metalloids or non-metallic elements called silicon, which can be isolated as a dark brown powder. Sand, flint, and quartz consist almost entirely of silica. So do the granitic and siliceous rocks which form so large a portion of the earth's crust. The highest and most extensive mountain ranges are huge masses of silica, and the deserts of Africa and Asia are vast plains of the same abundant substance. Silica forms the sand and shingle of the seashore and enters into the composition of every soil. It is the chief ingredient of some of our most precious jewels, of the invaluable transparent glass, and of the stones with which we pave our streets and build our temples. Alumina is a compound of oxygen and a very extraordinary metal named aluminium, of which we shall have to speak in another of our fairy tales. Alumina is the basis of every kind of clay, and is only second in importance to silica. It is also a constituent of our rocks and soils, and of our gems and our building materials, and we make use of it to form earthenware, a substance which rivals glass in usefulness. Lime is another abundant metallic oxide or rust, its base being calcium, a beautiful silver-white metal, which burns brilliantly when heated in the air. In nature, lime is generally found in combination with carbonic acid, one of the constituents of the atmosphere. The well-known substance chalk, which forms our far-famed white cliffs, the compact limestones used in architecture, and all the elegant varieties of marble are examples of this union. The solid portions of our globe are almost as rich in oxygen as the atmosphere and ocean. Every rock is a compound of oxygen with certain metallic and non-metallic bodies. Silica contains about half its weight of this abundant element, alumina no less than 1/3, and lime 2/5. In some compounds oxygen is replaced by another metalloid. Common salt, the chief saline matter of seawater, is a compound of sodium, a metal closely allied to potassium, with chlorine, a remarkable gaseous body which in some respects resembles oxygen. The glistening yellow mineral called iron pyrites contains iron and the metalloid sulfur. The variegated crystalline substance known as fluorspar is a compound of calcium, the metallic base of lime, with fluorine, a mysterious body which the chemist has never yet been able to procure in a separate state. The so-called noble metals, namely gold, silver, mercury, platinum, and a few others, are usually found in a state of purity. Sulfur is frequently met with uncombined, and carbon is found pure in the diamond. With these few exceptions, the material world may be said to be an assemblage of compounds formed by the union of 13 metalloids with 50 metals. Plants and animals are almost wholly composed of oxygen, hydrogen, nitrogen, and carbon. Hence these metalloids have been styled the organogens, or organ-forming elements. The chemist tells us that wood, sap, starch, muscle, blood, nerve, and all other organized substances result from the combination of these four principles in varying proportions. Vegetables feed upon inorganic matter. They derive their carbon from carbonic acid, their nitrogen from ammonia, and their oxygen and hydrogen from water. Animals are dependent upon the vegetable kingdom for their sustenance. A large number of races feed directly upon herbs and fruits. Others prey upon the bodies of these vegetable feeders. When animals die, their bodies suffer decomposition, and their original constituents, water, ammonia, and carbonic acid, return to the atmosphere to nourish another generation of plants for another generation of animals to feed upon. The elements are indestructible, and death merely alters the arrangements of their atoms. The ancient philosopher contended that all things were formed out of 4 elements. The modern philosopher declares that the 2 great organic kingdoms spring from a few invisible gases. The theory seems almost as credible as the fact. The following words from the pen of a celebrated chemist, Liebig, read like the page of some wild romance, and yet they deal with facts that are incontrovertible. Man is formed of condensed air, or solidified and liquefied gases. He lives on condensed as well as uncondensed air, and clothes himself in condensed air. He prepares his food by means of condensed air, and by means of the same agent moves the heaviest weights with the velocity of the wind. But the strangest part of the matter is, that thousands of these tabernacles formed of condensed air, and going about on 2 legs, occasionally, and on account of the production and supply of those forms of condensed air which they require for food and clothing, or on account of their honour or power, destroy each other in pitched battles by means of condensed air. We have now arrived at a true solution of the great problem. What is the world made of? The 3 kingdoms of nature are built up of some 63 elementary bodies, endowed with the most diverse properties and affinities, each being destined to perform some important part in the great system of creation. Truly has it been said that the powers of not one element could be modified without destroying at once the balance of harmonies, and involving in one ruin the economy of the world. Although the ancient doctrine of the 4 elements has been exploded by chemistry, we must still honour the mighty sages by whom it was propounded. The doctrine is not wholly false, and were we to confine our observations, as they did, to the external properties of matter, we should be forced to acknowledge the justice of their conclusions. In some sense the world is really made up of the 4 elements. Fire may be said to represent the imponderable agents, heat, light, and electricity. The remaining elements, the 3 physical states of ponderable matter, namely the gaseous, liquid, and solid. The difference between our present views and those of the ancients consists in this. We regard these states as mere modes of existence, while they believe them to be distinct principles. We must now take leave of the 4 elements, as we fear our readers are growing impatient for another story from the plenteous budget of science. End of chapter 3. Chapter 4 of the Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. The Life of an Atom. Why may not imagination trace the noble dust of Alexander till he find it stopping a bunghole? Hamlet. The particles of matter are subject to strange vicissitudes. Every atom has its peculiar history. In all probability, the countless molecules of carbon, oxygen, and hydrogen, which are aggregated into this lump of white sugar, met together for the first time in the juice of the cane. Where were they before the sugar cane was planted? Who can tell? One of these atoms of carbon may have coursed through the veins of a Hottentot. Another may have existed in the brain of a Laplander. The old story-tellers never scrupled to endow inanimate objects with the faculty of speech. Let us follow in their footsteps, and create a talking atom. Such a gifted entity might thus recount his adventures in the 3 kingdoms of nature. I am an atom of carbon. The members of my family are innumerable, and are disseminated throughout the universe. Some of my brethren are grouped together in those diamonds which are so much prized by the strange atomic fabrics called human beings. These jewel-forming atoms are much to be pitied, though they give themselves great airs, and sneer at their unaristocratic relations. I would 100 times rather be the roving atom that I am, than one of the molecules of the Koh-i-Noor itself. When the world was young, I led a very steady life. I remember forming part of a huge mass of rock which was built up of atoms of carbon, oxygen, and calcium, known as limestone or carbonate of lime. For ages I never saw the light, and remained in ignorance as to the existence of anything besides the atoms which surrounded me. Fortunately, I was situated very near the surface of the rock, and in course of time the atoms above me were removed, probably by the drops of water which fell from the heavens. Never shall I forget the delight I experienced on first beholding the outer world. I thought I should never be able to bear the brilliant sunlight, which dazzled me so that it was some time before I could make out the separate features of the scene. How beautiful, how grand everything seemed, and yet the landscape that was then unfolded before me was unenlivened by organic forms. There was not a tree to be seen, not so much as a blade of grass. Life had but just dawned upon the globe. The rock of which I was a constituent was part of an island, and from my station I could see the ever-restless ocean, whose atoms danced about so joyously that I longed to be among them. At the foot of the rock ran a little stream, which probably conveyed some atoms like myself into new scenes of existence. Night came on, and new wonders were revealed. Those marvelous celestial atoms, the stars, looked down upon me with their sparkling eyes, and the silvery light of the moon gave fresh grandeur to the ocean and my rocky island. As I gazed upon the glittering waters, I thought of my poor brethren who were deep down in the rock, and sighed. Next day the sun was obscured by clouds, and large drops of water fell from the sky. The stream became a river, and dashed through the valley at a headlong pace. The atoms constituting the raindrops buffeted me very severely, and at length their blows detached me, with a few old friends, from the mass of my brother atoms. The friends who clung to me in the hour of adversity were 3 atoms of oxygen and 1 of calcium. For countless ages we had been united, and now the raindrops, with all their bluster, could not sever us. No sooner were we detached than a stream of moving atoms impelled us down the sloping sides of the rock and hurled us into the river. There could be no rest for us there. The rapid current carried us through numerous valleys and gorges, and finally launched us into the ocean. We now began to lead a new kind of life. The atoms of the ocean were not fixed, like those of the rock. They glided over each other with perfect ease, and were continually in motion. As a matter of course, these atoms communicated their motion to us. It would be impossible for 5 little molecules to stand still while myriads were pushing them. We performed some wonderful voyages during the ages that we spent among the oceanic atoms. Sometimes we passed from the equator to the poles, but our usual course was from west to east, in which direction a mighty stream of atoms constantly flowed round the globe. A strange mishap forced us to relinquish our roving habits. In traversing a chain of rocks, we were sucked into the stomach of a tiny plant-like animal, the coral polyp, whose frame was built up of numberless atoms, most of them members of the carbon family. A place was found for us in this living organism beside certain atomic groups, each composed of 5 individuals exactly like ourselves. In course of time, the vital force which had aggregated the various molecules into such a wondrous system ceased to act. In other words, the animal died. The atoms which formed the soft portions of the body now began to change their position, and in a very short time they were all carried away by the wandering atoms of the ocean. As for me, I was still surrounded by my 4 friends, and still associated with numerous 5-fold groups. The creature who had robbed us of our liberty was now no more, but for all that we were unable to move. We were fixed to the rock upon which the organism had flourished. Indeed, incredible as the statement may appear, the entire reef, which extended for some hundreds of miles, was composed of atoms that had been snatched from the ocean by innumerable generations of these gelatinous little animals. The barrier reef along the north coast of Australia is composed of a chain of coral rocks, and is more than 1,000 miles long, and from 10 to 90 miles in breadth, while it rises from depths which in some places certainly exceed 1,800 feet. What a mausoleum for creatures so low in the scale of being! I cannot say how long I existed as a constituent of this marine rock. An atom takes no heed of time, and a few millions of years pass by very quickly. Time affects only those compound entities called plants and animals. The surface of the earth underwent some strange mutations while I was a rock atom. The relative position of land and water changed. Mountains were upheaved by the internal fires of the globe, and deep valleys were eroded by rivers. The waters of the ocean receded from the reef to which I belonged, and left it high and dry, as a chain of hills in the interior of a vast continent. None of these changes, however, disturbed my repose. The ties which bound me to my fellow atoms seemed indissoluble. At length, the rock of which I was a constituent was subjected to a new mutation by volcanic agency. The pent-up fires of the earth burst through the ancient reef, and liberated myriads of its component atoms. For some time I remained unaffected by the commotion, but eventually I felt the disturbing effects of the intense heat, and found that my bonds were loosened. I was no longer a rock atom, and the ascending stream of fiery particles bore me into the atmosphere. As for my old companions, who had hitherto shared my reverses, only 2 of them attended me now, for the atom of calcium had persuaded one of the atoms of oxygen to remain with him in the rock. The metal was not fitted for an aerial life, and did not care to be separated from all his friends. What a marvellous difference the absence of those 2 atoms made in the group to which I belonged! When there were 5 of us, we constituted a solid molecule. Now we formed a compound gaseous atom, carbonic acid. Who can describe the joys of an aerial atom? I have never yet been part of a poet's brain, and it is therefore quite out of my power to set forth in appropriate language the varied pleasure of an atmospheric existence. My roving life as an atom of the ocean had its charms, but it was not to be compared with the life I now led among the sportive atoms of the air. My 2 friends remained true to me. Indeed, had it not been for their constant watchfulness, I should have fallen to the earth, for I was not buoyant enough to float unsupported. Sometimes we soared to a great height, where the aerial atoms were very far apart, but we usually kept near the surface of the earth. How changed was the aspect of nature! When I first beheld the outer world, all was barren and lifeless. Now every scrap of dry land was covered with a luxuriant vegetation. This was the Carboniferous period. The plants were mostly of great magnitude, though, strange to say, some of them were closely allied to the humble ferns and tiny mosses of the age of man. I have seen many wondrous things in my time, but nothing to surpass those ancient forests, composed of ferns as large as oaks and mosses 70 feet high. I was destined to become part of one of these gigantic mosses. As I was passing through a forest with myriads of aerial atoms, I happened to strike against a leaf, which instantly absorbed me, but allowed my 2 companions, who had never been separated from me before, to pass on with the rest. For some time I circulated through the vessels of the living plant as a constituent of the sap, but at length I settled down among the atoms of carbon, oxygen, and hydrogen which were aggregated into particles of wood. Such are the vicissitudes of an atom, now literally as free as the air, now a captive in the tissues of a living organism. A second time the hidden processes of life had compelled me to part with my liberty. I have already alluded to the mutability of the earth's surface. The disturbances that took place during the time that I was a vegetable atom were of a very extraordinary character. The group of islands upon which the monster ferns and mosses flourished sank beneath the waves, and in course of time they became overlaid with beds of rock, formed by the deposition of sand, clay, and other materials at the bottom of the ocean, the sedimentary matter being hardened by heat and pressure. Human beings talk about the stability of the earth, but we atoms know very well that its great characteristic is instability. Why? The crust of this so-called immovable earth is continually bulging out in some places and falling in others. I did not lead a very merry life in the depths of the earth, but still I did not repine. Experience has taught me that I was a creature of circumstance, and must submit to my destiny. How long I remained underground I cannot say. Millions of years may have flown by, but they brought me no change. Numberless atoms of oxygen and hydrogen that were associated with me in the living plant forced their way between the molecules of the overlying rocks, and thus escaped from their subterranean prison. I was too firmly attached to my solid brethren to accompany these adventurous atoms, so I waited patiently for succour, assured that it would come sooner or later. My deliverance was effected by the agency of man, that wondrous being, partly composed of atoms like myself, and partly of an immaterial spirit, who now reigned supreme over the other organisms of the world. Having found that coal, the compressed remains of the ancient forests, could be made to yield light and heat, agents which greatly contributed to his happiness, he sank deep pits through the rocks and transferred me, with myriads of my brethren, from the earth's gloomy depths to its sun-gilt surface. Now commenced the eventful period of my life. Hitherto my transitions had been few. Twice had I been a constituent of stone, twice a part of a living organism. I had tasted the pleasures of a marine existence. I had floated joyously in the air. I had lain for ages in the bosom of the earth. But in the few short years that have elapsed since my release from bondage, I have passed through a far more wonderful series of changes. Let me now recount the chief incidents of my modern career. I will make use of as few words as possible, lest my narrative should be cut short by a new alteration in my condition. Soon after my arrival at the surface of the earth, I was separated from my brother atoms by the process of combustion, and carried aloft by two members of the great oxygen family. My freedom was of short duration. Nature had set innumerable traps for me, in the shape of living organisms, and by one of them I was soon made captive. I now became a part of a grain of wheat, and in course of time I found myself in the stomach of a man. In the human frame I passed through a definite course of vicissitude, and was then breathed forth to make room for a newcomer. Once more I enjoyed the pleasures of an aerial life, which, I need scarcely say, were again shared by two atoms of oxygen. From the atmosphere I passed into the substance of a tree, which was destined to fall by the hand of man soon after my absorption. By a cunning process the wood was decomposed, its volatile atoms of oxygen and hydrogen were set free, and an aggregate of carbon atoms or charcoal remained. Man had not yet done with me and my dusky brethren. He had separated us from our companions in order that we might be at liberty to unite with certain atoms of iron, and thus produce a substance, steel, which he greatly prized. This strange union was effected, and in course of time I became part of one of those weapons with which man destroys his fellow man. I now witnessed some fearful scenes of bloodshed, and being an atom of a philosophical turn of mind, I often speculated upon the motives that induced those short-lived atomic structures called men to hasten each other's dissolution. When I speak of these scenes as fearful, I make use of a human expression, for I need scarcely say that death can have no terrors for an undying atom. I was detached from the metallic mass by the agency of heat, and two friendly atoms again conveyed me into the atmosphere. My next transition was into the juice of a grape, where I remained in peaceful retirement, until man induced me to become a constituent of a bright and sparkling liquid, champagne, which he confined in strong glass bottles. How long I remained a prisoner I cannot say, but as soon as my bottle was opened, I made my escape in a bubble of gas. After a short flight through the air, I passed into a blade of grass, and thence into the huge frame of an ox. The next change in my condition was brought about by human agency, and I became a constituent of a volatile and colourless liquid, prussic acid, which was such a terrible poison that a few drops of it would suffice to kill the largest animal. Now, it so happened that a foolish man swallowed a small quantity of this liquid. He grasped the little vial which contained the poison with a trembling hand. He raised it to his lips, and in another moment I found myself in his lifeless body. A simple atom can form no idea of the motives which induce composite beings to perform certain actions, but as far as I can judge, this self-destruction seems to be unworthy of a being like man. When I escaped from the dead body, I passed into the vegetable kingdom, where I became a part of a beautiful flower. Soon after, I found myself in the body of a bee, and in course of time I became a constituent of one of the waxen cells which the little artisan had so cleverly constructed. From the honeycomb I passed into a wax taper, from which I was released by the process of combustion. It was now my lot to spend some time among the aerial atoms, but at length I came in contact with the sugar cane, and became a constituent of the sweet juice from which the lump of sugar was extracted. Such is the story of my life, or rather a fragment of my life. I enjoy perpetual youth. To-day I may be buried in a mass of corruption, but to-morrow I may form a part of a newly opened rose. Time cannot reach me. His hourglass may be broken, and his scythe may be shattered, but still I shall exist. At the present moment I am joined to countless atoms, indestructible and eternal like myself, in a fragment of sugar. But who can tell where I shall be in a year's time? This peroration has been cut short by our firstborn, who has run away with the lump of sugar, and we have every reason to believe that the atom is undergoing new transitions. End of chapter 4. Chapter 5 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. A little bit. Many a little makes a mickle. Old proverb. In the foregoing pages we have assumed that all things are made up of very little bits, called atoms. This view of the nature of matter is purely conjectural, but it agrees so well with the truths revealed by science that we must admit it to be highly probable. Let us descend for a while from the realms of imagination and lay before our reader the facts upon which the beautiful theory of atoms is based. The word atom is derived from the Greek language, and signifies that which cannot be cut, a very appropriate term, for an atom being the smallest possible particle of a substance must necessarily be indivisible. The existence of half an atom is inadmissible, because the mind cannot form an idea of a particle smaller than the smallest. Philosophers are divided in their opinions respecting the nature of the ultimate particles of matter. Some maintain that they are hard and solid, and therefore of a definite size and weight, though so minute as to defy all our optical instruments to enable us to perceive them. Others hold them to be mere points or centres of force, destitute of solidity and magnitude. What is an atom? This is a problem which the human mind can never solve. It can only throw out shrewd guesses at the truth. We will, however, take it for granted that the ultimate particles of matter are indivisible and indestructible, without wasting our time on metaphysical subtleties. Though we can form no conception of the absolute size of atoms, the wonderful divisibility of matter furnishes many proofs of their extreme minuteness. The gold beater hammers out a single grain of the precious metal until it covers 49 square inches. Now, each square inch of this gold leaf may readily be cut into 100 strips, and each strip into 100 pieces, each of which is distinctly visible to the unaided eye. A single grain of gold may thus be subdivided into 490,000 visible parts. But this is not all. If attached to a slip of glass, the leaf may be subdivided still further, as 10,000 lines may then be ruled into the space of a square inch, and in this manner the entire leaf, weighing but a grain, may be cut into 4,900,000,000 fragments, each visible by means of the microscope. As we require no less than 10 figures to express the number of parts into which a grain of matter may be subdivided by mechanical means, and as each of these parts must contain a vast number of particles, we see that an atom must be a very little bit indeed. But gold furnishes a still more remarkable instance of the extension of matter. A gilt wire used in embroidery is formed by extending gold over the surface of silver. A very little gold is made to go a very long way, for each grain is spread over a surface of nearly 10,000 square inches. In the animal and vegetable kingdoms we meet with some surprising instances of the divisibility of matter. The microscope reveals the existence of animals so wonderfully minute that it takes 100 millions of them to weigh a grain. Yet each creature is possessed of distinct organs, and must be composed of innumerable atoms. The spores of the lycoperdon, or puffball, are found to be little orange-colored globes, and although each spore is capable of becoming a living plant, no less than 125,000 of them would be requisite to form a single globe of the diameter of a human hair. The sense of smell enables us to perceive particles of whose magnitude we can form no adequate conception. Odor is simply the disengagement of the volatile particles of a substance, yet a single grain of musk has been known to perfume a huge room for the space of 20 years. We may rest assured, then, that the atoms of matter are exceedingly minute, though their actual size can never be determined by our powers of perception. Let us now consider the aggregation of these little bits into masses. The force which holds the atoms together is called cohesion. It is greater in solids than in liquids, while in aeriform bodies it seems to be altogether absent. We have every reason to believe that the ultimate particles of a body are never in actual contact, but are placed at a certain distance from each other, so that there exists around every individual particle a space void of matter. All bodies are more or less compressible, and unless we acknowledge the existence of these empty spaces, we must suppose that two or more particles are capable of occupying the same place at the same time, a supposition which is opposed to the notion of an atom having a definite size. A volume of air can be compressed into a space 1,000 times smaller than that which it originally occupied, and we must therefore conclude that the atoms of air are separated by wide intervals. Solids and liquids must also have interstices or pores between their particles, as they invariably expand when heated and contract when exposed to a low temperature. The porosity of gold was demonstrated some 200 years ago by the famous Florentine experiment. A hollow ball of the precious metal, filled with water, was submitted to a great pressure, by which the fluid was made to ooze through its pores and bedew its outer surface. The distance between the particles of matter is greater in liquids than in solids, and greatest in gases and vapours. It is highly probable that all bodies, even the densest metals, contain more space than matter. In other words, that the atoms are much smaller than the spaces which separate them. Some of our greatest philosophers have held the atoms of matter to be immeasurably small compared with their surrounding spaces. Newton thought that the whole material world might be compressed into the space of a single cubic inch, provided that its particles could be brought into actual contact. Sir John Herschel compares a ray of light penetrating glass to a bird threading the mazes of a forest, and says that there is no absurdity in imagining the atoms of a solid to be as thinly distributed through the space it occupies as the stars that compose a nebula. We need scarcely say that these hidden truths do not fall within the sphere of scientific inquiry, but can only be subjects for the exercise of speculation. All our instruments are far too clumsy to help us to a knowledge of atomic magnitudes. The compasses that can measure the interval that separates particle from particle, and the scale that will turn with the weight of an atom, do not belong to man, though the imagination may picture such delicate contrivances in the laboratory of a scientific fairy. These considerations lead us to a subject about which we do know something, namely, the relative weights of the ultimate particles or atoms of bodies. Chemistry has revealed the existence of some 63 elementary bodies, or, according to the atomic theory, 63 different kinds of atoms. Now, although we cannot ascertain the actual weight of a single atom, we have good grounds for believing that an atom of oxygen is heavier than an atom of carbon and lighter than one of sulphur. Before we enter into this subject, we have a few words about the great man who revived the ancient theory of atoms and made use of it to explain the mysterious laws of chemical combination. John Dalton was born in Westmoreland in the latter portion of the last century, and belonged to the sect of Quakers. When very young, he resided with Mr. Gough of Kendal, a blind philosopher, to whom he read, and whom he assisted in his scientific investigations. It was here that he acquired a considerable part of his education, particularly his taste for mathematics. From Kendal, Dalton went to Manchester, and commenced teaching elementary mathematics to young men. In this way, together with a few courses of chemical lectures which he occasionally delivered, he contrived to support himself during a long and useful life. His slender income was always equal to his wants, and in his contempt for riches he resembled the sages of antiquity. His kind heart and powerful mind gained him many friends and admirers, and in course of time he came to be regarded as a great philosopher, though he still continued to earn his bread as a tutor. Such was the founder of the beautiful atomic theory of chemistry, which is so well adapted to render certain natural laws intelligible to our understanding. In examining the so-called four elements, we alluded to the fact that bodies united to form compounds in definite proportions. Let us explain this matter more fully. Water invariably contains oxygen and hydrogen in the proportion of 8 parts by weight of the former element to 1 part of the latter, whether these parts represent tons, pounds, grains, or any other quantities. The whole of the oxygen contained in the ocean is exactly 8 times heavier than the hydrogen with which it is combined, and the weights of the two gases bear the same relation to each other in the dewdrop. If we take another chemical compound, we shall find that the proportions by weight of its constituents are invariable. Thus, there is a broad distinction between such a compound and a mere mixture in which the ingredients are present in indefinite proportions. Water is not the only compound that can be formed of oxygen and hydrogen. We can compel 1 part of hydrogen to combine with 16 parts of oxygen, and the result of their union is a colourless liquid, less volatile than water and having a metallic taste. This liquid, called peroxide of hydrogen, and water are the only compounds that can be formed of the two gases. This fact is well worthy of consideration. Hydrogen will combine with 8 or with 16 parts of oxygen, but in no other proportions. Let us now glance at some other compounds. The poisonous gas known as carbonic oxide contains 6 parts of carbon and 8 of oxygen. But 6 parts of carbon can also combine with 16 of oxygen to form carbonic acid. Again, in ordinary coal gas, we find 1 part by weight of hydrogen united to 6 of carbon. How can we account for these recurrent numbers? What relation subsists between the number 8, or its multiple 16, and oxygen, between 1 and hydrogen, between 6 and carbon? Why should these 3 bodies combine in fixed numerical proportions? According to the beautiful atomic theory of Dalton, these numbers express the relative weights of the ultimate particles of matter. Let us consider the composition of water in this light. The smallest possible particle of water is composed of 1 atom of hydrogen gas and 1 atom of oxygen, the latter being 8 times heavier than the former. Now it is evident that whatever may be the number of particles in a given volume of water, the relative weights of the two gases will remain constant. The smallest particle of the peroxide of hydrogen contains 1 atom of hydrogen and 2 atoms of oxygen. Accordingly, there can be no compound of hydrogen and oxygen between water and the peroxide, unless we admit the existence of half atoms. We have only spoken of 3 of the elementary bodies, as we wished our remarks to be as simple as possible. Each of the 63 elements has, however, a definite combining proportion, or atomic weight. How admirably this atomic theory explains the laws of chemical combination! How intelligible it renders those fixed, invariable weights in which the elements unite to form compounds! All is shown to depend on the properties with which those inconceivably small particles of matter are invested. We have told the reader all we know about atoms. At least all we think we know, for we can never be certain that atoms exist. They are immeasurably minute, they are separated from each other by wide intervals, and they have a definite weight. A German chemist has endeavoured to render the atomic theory intelligible by a very ingenious illustration. He compares atoms to heavenly bodies, which, in comparison with the extent of the space in which they are suspended, are infinitely small, that is, are atoms. Innumerable suns, with their planets and attendant satellites, move in infinite space, at definite and measured distances from each other. They are individually indivisible, inasmuch as there exists no force capable of separating them into parts, tearing off from them anything material, or altering their size or form in such a degree as to be perceptible, or to impair or disturb their relations to the other heavenly bodies. In this sense, the whole universe coalesces into one immense body, the atoms of which, that is, suns, planets, and satellites, are indivisible and unchangeable. There are many things in nature which the human mind will never be able to comprehend, and foremost among them we must place our little bit. End of chapter 5. Chapter 6 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. Modern Alchemy. But when you see the effects of the great medicine, of which 1 part projected on 100 of Mercury or Venus or the moon, shall turn it to as many of the sun, nay, to 1,000, so ad infinitum, you will believe me. Ben Jonson. Who has not heard of the Philosopher's Stone, that much coveted but unattainable red powder of the alchemists, which was supposed to possess the powers of transmuting baser metals into gold, of healing disease, and of restoring youth? Who has not read of those misguided men of former ages, whose lives were passed in attempting to discover this precious substance, which was to confer upon them inexhaustible wealth, health, and longevity, but whose labours too often resulted in poverty, sickness, and death? In the present day we are too apt to regard the doctrine of transmutation, which formed the basis of alchemy, as a mere hallucination of the human mind, and to look upon the men who entertained it with mixed feelings of pity and contempt. Now, if we only take the trouble to dip into the subject of alchemy, we shall find that the idea of the transmutation of baser metals into gold stood in the most perfect harmony with all the observations and all the knowledge of the age in which it was conceived, and that the alchemists, instead of being crack-brained enthusiasts, were the most learned and acute men of their time. In the 16th and 17th centuries there were many impostors who pretended a knowledge of gold-making, but it is unjust to confound them with the true alchemists, who were equivalent to the chemists of the present day. We cannot really draw a line of demarcation between alchemy and chemistry, as the one science passed by an imperceptible transition into the other. Alchemy is ancient chemistry, and chemistry modern alchemy. Many of the opinions entertained by the chemists of to-day are quite as extravagant as those held by the alchemists. Indeed, as our knowledge increases, the transmutation of metals seems to grow more and more probable. Before we consider the magical transformations that are effected by the modern alchemist, let us examine some of the doctrines propounded by his ancient representative. The alchemists maintain that all metals are compounds, that the baser metals contain the same constituents as gold, contaminated with various impurities. To transmute any metals into gold, these impurities must be removed or remedied, a result only to be attained through the agency of the great medicine, or philosopher's stone. This view of the nature of metallic bodies was perfectly consistent with known facts. It was known that the color or hardness of a metal could be modified by the addition of a foreign substance, and it was only natural to suppose that the different qualities of the metals depended on certain impurities. Gold was the only pure or healthy metal. Brass was diseased gold, mercury was diseased silver, but these metals and all the others might be healed or transmuted into gold by the wonderful red powder. In the mystical language of the alchemists, gold was called Sol, or the sun, silver being the next metal impurity was Luna, or the moon, and the other 5 metals then known received the names of the planets. The idea that the philosopher's stone possessed the powers of curing diseases and of prolonging life was evidently suggested by its supposed effect on ignoble metals. Since it could heal the metallic lepers and convert them into gold, why should it not ennoble the human body? The existence of the philosopher's stone was never questioned, though few of the alchemists who have left writings behind them boast of having had it in their possession. In all the wonderful stories that are told of the conversion of the baser metals into gold, some mysterious unknown is made the fortunate possessor of the magical substance. The narrative of Helvidius, the distinguished physician to the Prince of Orange, is a good example of these stories. At the close of the year 1666, a stranger called upon Helvidius, and showed him 5 large plates of gold, which he said he had made by means of the philosopher's stone. The physician, who had hitherto been a bitter opponent of alchemy, was not prepared to receive this extraordinary statement without some convincing proof of its truth. He therefore besought the stranger to give him a small portion of the stone, or at least to make a trial of its powers in his presence. The stranger refused to accede to either of these requests, and took his leave, promising, however, to return in 6 weeks. He kept his promise, and presented Helvetius with a piece of the stone about the size of a mustard seed. Next day the physician, in the presence of his wife and son, put 6 drachms of lead into a crucible, and as soon as it was melted, threw into it the fragment which he had obtained from the adept. The crucible was now covered with its lid, and left in the fire for a quarter of an hour, at the end of which time the whole of the lead was converted into gold. The melted metal was at first of a deep green color, then it became blood red, but when cold it assumed the true tint of gold. This ingot stood all the tests that were applied to it by Porelius, the warden of the Dutch mint, and was found to be pure gold. We need scarcely add that the sceptical Helvetius became a firm believer in the transmutation of metals. We dare not accept this strange story as a true one, though we cannot comprehend the motives that could have induced Helvetius to promulgate that which he knew to be false. In the present state of our knowledge, we regard lead and gold as distinct bodies, and not modifications of the same substance. If the alchemists failed to discover the philosopher's stone, we must not conclude that their labours were fruitless. In seeking that which had no real existence, they found some inestimable treasures, for most of those acids, alkalis, and salts that are indispensable to the modern experimentalist were discovered hundreds of years ago by the alchemists. The philosopher's stone, says Baron Liebig, for which the ancients sought with a dim and ill-defined impulse, was in its perfection nothing else than the science of chemistry. Is that not the philosopher's stone which promises to increase the fertility of our fields, to ensure the prosperity of additional millions of mankind? Does not chemistry promise that instead of 7 grains we shall be enabled to raise 8 or more on the same soil? Is that science not the philosopher's stone which changes the ingredients of the crust of the earth into useful products, to be further transformed by commerce into gold? Is that knowledge not the philosopher's stone which promises to disclose the laws of life, and which must finally yield to us the means of curing diseases and of prolonging life? With these remarks we will take our leave of the ancient alchemists, and proceed to consider the labours of the alchemists of the present day. Let us step into a laboratory, and surprise one of these men of science at his work. What a different place from the smoky workshop of the alchemist of former days! The massive furnaces have given way to cunning contrivances for gas, and all the clumsy alembics, aludels, and earthen vessels which were once in vogue have been displaced to make room for tiny bottles, retorts, glass tubes, and balances. The alchemist himself has shaved off his long beard, and has discarded his ample gown. He now wears a most unpicturesque black coat, and looks for all the world like an ordinary person. What is he doing? Is he trying to transmute lead into gold? No. He is not satisfied that the metals are transmutable, and he cannot afford to waste his life in researches which may never lead to satisfactory results. He is doing something that seems quite as extraordinary as gold making. He is extracting a beautiful metal from clay. This metal, which is called aluminium, was first procured in a separate state some 30 years ago, but in so small a quantity that its peculiar qualities could not be defined. We are indebted to a celebrated French adept, M. St. Clair Deville, for the process by which the metal can be obtained in considerable masses. Here is a bar of aluminium. It resembles silver in its beautiful luster, but can be easily distinguished from that metal by its bluish color. If we handle the bar, we shall marvel greatly at its lightness, as aluminium is only 2½ times heavier than water, or less than 1/3 the weight of iron. The alchemist will tell us that it is endowed with many striking properties. It can be fused almost as easily as zinc, and cast into any form. It is malleable and ductile to a great extent, and can be beaten into the thinnest plates, or drawn out into the finest wires. It is a better conductor of electricity than any metal at present known. It does not tarnish on exposure to the air, and is not affected by the sulphurous vapours that prove so destructive to the lustre of silver. It is admirably adapted for the manufacture of bells, as it has all the sonorous qualities of the most expensive bronzes. Its marvellous lightness and strength render it an invaluable material for defensive armour. It is free from deleterious qualities, and therefore suited for domestic utensils. It may be fashioned into ornaments that will never lose their splendour, and into delicate scale beams and watch wheels that will never be affected by rust. In fine, aluminium seems to possess properties which render it useful in 1,000 ways, and if the process by which it is obtained can be further simplified, It will prove an inestimable boon to mankind. The source of aluminium is inexhaustible, since it is the base of every kind of clay. About 1/3 of the weight of every brick, every stone jar, and every teacup consists of this curious metal. Who will say that alchemy is extinct? What science but alchemy would enable us to extract a metal having an intrinsic value equal to that of gold from a lump of worthless clay? The artificial formation of lapis lazuli is another brilliant achievement of modern alchemy. This mineral has always been esteemed for its beautiful azure blue color, and for furnishing us with the valuable pigment ultramarine. Before the chemist could produce ultramarine artificially, he required to know the composition of the natural mineral. Before he could form a portion of lapis lazuli, it was necessary that he should pull another portion to pieces for a pattern. This preliminary operation was soon performed, and lapis lazuli was found to be composed of silica, alumina, and soda, 3 colorless bodies, with sulfur and a trace of iron, neither of which is blue. The chemist was not a whit disheartened at the absence of any coloring ingredient, as he knew that it was impossible to account for the color of most chemical compounds. He now combined the 5 ingredients of the mineral in their proper proportions, and saw, to his great delight, that the compound assumed the matchless hue of ultramarine. The artificial ultramarine is even more beautiful than the natural, while for the price of a single ounce of the latter we may obtain many pounds of the former. Surely our modern alchemists have discovered the true philosopher's stone, for with the comparatively valueless substances, flint, clay, soda, sulfur, and iron, they form a mineral which was formerly much dearer than gold. We cannot tell what wonders may yet be performed by the modern alchemists. One of their number has said that tomorrow or next day someone may discover a method of producing, from a piece of charcoal, a splendid diamond, from a bit of alum, sapphires or rubies, or from coal tar the beautiful coloring principle of madder, or the valuable remedies known as quinine and morphine, all these things being either as precious or more useful than gold. The extraction of aluminium from clay and the manufacture of ultramarine are examples of chemical analysis and synthesis, but not of transmutation. Let us now examine the opinions entertained by the alchemists of today on the subject of transmutation of elementary bodies. The ancients believed the metals to be compounds, and this view may be correct. They are now considered to be simple substances, not because they are known to be undecomposable, but because they have never yet been decomposed. 50 years ago, upwards of a dozen bodies were regarded as elements, which are now known to be compounds of metals with oxygen. Who can tell what another period of 50 years may do for alchemy? It is quite possible that at the end of that time the 63 so-called simple bodies may be found to be mere modifications of 3 or 4 elements, or perhaps of one primordial substance. These considerations lead us to reflect on the curious transformations which occur in the properties of certain elementary bodies, and which must be regarded as instances of transmutation. Now, a difference in the properties of 2 compounds having the same composition may arise from a difference in the arrangement of their ultimate particles, but how is it with the different forms assumed by a simple body? A mass of phosphorus is supposed to be an aggregate of similar atoms, yet this and many other substances of a simple nature are liable to strange variations of condition which we are as yet unable to explain. The element carbon exists in many different states. This irregular lump of charcoal, this light powder called lampblack, and this hard semicrystalline mass of coke are mere modifications of one substance. Again, this piece of graphite is chemically the same substance, as it is simply an aggregate of carbon atoms, but it has none of the properties of charcoal. It has a metallic leaden-grey luster, whence its familiar name of black lead. It burns with great difficulty. It is greasy to the touch, and it leaves dark traces when rubbed upon paper. But the most remarkable form assumed by carbon is that of the diamond. This precious gem occurs in nature in regular crystals, usually colorless, but sometimes yellow and brown. Now we are convinced that this brilliant and transparent body is made up of the very same atoms as those which go to form the dull black mass of charcoal. The alchemist has not yet succeeded in making diamonds, but he has already transmuted diamonds into coke. Who knows but what he may reverse this transmutation before long? When we find a single element assuming these protean shapes, we must admit that the notions of the old alchemists were far from being extravagant. To a person ignorant of chemistry, it would appear much more probable that the metals are modifications of one substance, than that the diamond is merely crystallized charcoal. Sulphur may be obtained in various forms. The roll sulphur or brimstone, and the fine powder called flowers of sulphur, are probably the only forms known to the reader. The alchemist, however, procures sulphur in beautiful semi-transparent crystals, in needle-like prisms of a brownish-yellow color, and in a soft, sticky mass, which may be drawn out into elastic threads, and which greatly resembles shoemaker's wax. Phosphorus is equally changeable, and may be obtained in no less than 5 different forms. Let us compare ordinary phosphorus with its most striking modification, which has been designated amorphous phosphorus. Ordinary phosphorus is a colorless, waxy-looking solid. The amorphous phosphorus is opaque and of a brownish-red color. The former is easily fusible, very inflammable, and luminous in the dark. The latter may be heated in the open air without change, until the temperature reaches 500 degrees, when it is converted into ordinary phosphorus. Great caution is required in handling the ordinary phosphorus, as the heat of the hand is sometimes sufficient to inflame it. But the philosopher who discovered the amorphous phosphorus, M. Schroeter, is in the habit of carrying this variety loose in his pocket. Common phosphorus dissolves in a bisulfide of carbon. The altered phosphorus is insoluble in that liquid. The former is very poisonous. The latter, in the same dose, has no effect on the animal system. These marvelous differences are inexplicable. We are able to change the ordinary phosphorus into the amorphous variety by means of heat, without adding to it any new substance. Therefore, we are quite sure that the soft, translucent solid that takes fire so easily is chemically the same substance as that uninflammable solid which looks like a piece of common red sealing wax. Were we unable to effect this strange transmutation, we should doubtless regard these 2 modifications of phosphorus as distinct elements. The invisible gas, oxygen, can be made to assume a very strange condition by transmitting it through a succession of electric sparks. This altered oxygen, which has received the name of ozone, exhibits some very striking properties. It has a powerful odor, whereas ordinary oxygen is destitute of the slightest smell. It possesses considerable bleaching powers, corrodes organic matters, and acts as a powerful oxidizing agent. It seems to be much more active than ordinary oxygen, and might easily be taken for a distinct element by those ignorant of the fact that its active character can be destroyed by heat. These instances of actual transmutation will suffice to convince the reader that alchemy still exists. He will see that our modern alchemists are true descendants of the ancient gold seekers, though they no longer believe in the philosopher's stone. He will be less disposed to ridicule the idea of the transmutation of metals, and will be able to form some conception of the wonderful products of modern alchemy. End of chapter 6. Chapter 7 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. The Magic of the Sunbeam. The glorious sun stays in his course and plays the alchemist. King John. Wherever the sunbeam falls, we find life and motion, elsewhere death and stillness. Under its influence, the seed germinates, the stem sends forth branches, the leaf bursts from the bud, the flower unfolds its petals, and the fruit grows and ripens. This subtle agent plays an important part in many of the fairy tales of science. The philosopher has conducted it into his dark laboratory, and by twisting and torturing it with cunningly devised instruments, has forced it to reveal so many wonderful truths that the mind, in attempting to grasp them, is fairly bewildered. The magic of the sunbeam is indeed an inexhaustible theme, and we can only touch upon a few of its mysteries. Every sunbeam consists of light, heat, and chemical power, or actinism. At present we will consider the sunbeam as a ray of light, without regarding its other principles. What is light? This is one of those unanswerable questions that meet us on the threshold of every science. Some philosophers entertain the opinion that light consists of tiny particles of matter thrown off from a luminous body with prodigious velocity in all directions. Others suppose it to be an undulation or vibration produced in a medium called ether, which is believed to pervade all space. The former view of the subject is termed the theory of emission, the latter the undulatory theory. We cannot say which of these hypotheses or guesses approaches nearest to the truth, but undulatory theory has by far the greater number of supporters. Whether a ray of light be a stream of inconceivably minute particles of matter, or a succession of waves in an ethereal medium, we are quite certain that it travels at the rate of nearly 200,000 miles in a single second. But such is the disproportion between the distances of the celestial bodies that light must be about 8¼ minutes in reaching us from the sun, about 5 hours in coming from the planet Neptune, years from the nearest fixed star, and probably centuries from the nebulae. When we look up at the heavens, we do not see the stars as they are now, but as they were many years ago, for the light which now renders them visible must have left them long before we were born. Rays of light are emitted, under ordinary circumstances, in direct lines. They will not pass through a bent tube, nor turn a corner. Bodies through which light passes freely are called transparent, and those which do not admit it to pass, opaque. When light falls upon an opaque surface, a portion is absorbed and another portion reflected. When the reflected portion is considerable, the surface appears white, and black when the portion is inappreciable. We have said that a sunbeam consists of 3 great principles, namely light, heat, and actinism. These may be but modifications of one force, but in the present state of our knowledge it is better to regard them as distinct agents. Light acts upon the organs of vision, and enables us to distinguish external objects. Heat regulates the solid, liquid, and aeriform states of matter, and maintains this planet in the condition which is essential to the well-being of its inhabitants. Actinism brings about those wonderful chemical changes which are constantly occurring in nature. These 3 principles unite to form our magic sunbeam, just as 3 chemical elements unite to form a compound. How can we decompose a sunbeam? How can we separate those principles which are linked together in such a mysterious manner? Easily enough, for by the instrumentality of a triangular bar of transparent glass called a prism, the beam can be instantly resolved into its components. If a sunbeam, admitted into a dark chamber by a small hole in the window shutter, be allowed to fall on a prism, its subtle constituents are mysteriously disturbed, and precipitate themselves at different distances on a white tablet, or screen, placed to receive them. What marvellous change this is! A moment since the beam formed a bright spot on the screen, but now in place of the spot we see a lengthened band of variegated colours. On one side of the prism a pencil of brilliant white sunlight falls upon the surface of the glass. On the other, the pencil spreads out and paints upon the screen a ribbon whose beauteous hues infinitely surpass the colours that lie on an artist's palette. Examine these colours attentively. At the bottom of the band we find red, above it orange, then yellow, green, blue, indigo, and lastly violet. These colours pass by insensible gradations into each other, so that it is impossible to say where one colour ends and another begins. We have thus decomposed the visible principle of the sunbeam into its elementary colours, for our readers must know that white is a compound of 7 hues. The natural colours of bodies depend entirely upon the manner in which they decompose the sunbeams. A rose is red because its petals have the property of absorbing all the elementary colours of light except red, which it reflects. The pigments used by the artist are not, in themselves, colours. They are merely substances that absorb certain rays and reflect others. Our readers will now understand how it is that a body which reflects most of the light that falls upon it appears perfectly white. But we have not yet done with the variegated band, or prismatic spectrum, as it has been termed. If a highly sensitive finger were held in the yellow rays of the spectrum, a degree of warmth would be felt, greater than that if it were held in the violet rays. But if it were removed to the extreme red rays, a great deal more heat would be perceived than in either of the former cases. Now we have imagined the existence of a finger far more sensitive to slight variations of temperatures than ordinary fingers are, but these results have been obtained by means of very delicate thermometers or heat measurers. Let us now take a piece of paper, prepared for the photographic process, and place it upon the screen so that it may receive the rainbow-like colours upon its sensitive surface. On removing it, it will be found to be blackened at a point beyond the violet rays of the spectrum. The principle which blackens the prepared paper is actinism. From these experiments we learn that the sunbeam is an ethereal band of different rays, which may be separated by the instrumentality of the prism. We learn that heat is less refracted or bent by the glass than the other powers, as we find it but slightly thrown out of the right line which the beam would have taken had it not been interrupted by the prism. We discover that light is subject to greater refraction, as the 7 colors are thrown upon the screen above the maximum point of the heat rays. Lastly, we find that actinism is more refrangible than either heat or light, as we know that the maximum of this power is found in the upper part of the spectrum at a point where light rapidly diminishes, and where scarcely any heat can be detected. The analysis of the sunbeam by means of the prism must excite our wonder. Who would imagine that a simple wedge-shaped piece of glass would be able to separate those imponderable agents which reach us after having travelled 95 millions of miles together? We can isolate either of these solar principles without the aid of a prism. The crystal called black mica does not admit light to pass through it, but it is freely penetrated by heat, and on the other hand, glass stained green by oxide of copper offers scarcely any impediment to the passage of light, though it effectually stops the rays of heat. Again, a yellow transparent glass obstructs the chemical radiations, while a dark blue medium, which arrests nearly all the light, allows them to pass. Thus we see that the physical conditions of the 3 solar principles are essentially different. Let us now consider the magic influences of this sunbeam over the animal and vegetable kingdoms. The luminous principle first demands our attention, for although we are told that light is less abundant than either heat or actinism, we cannot help regarding it as the sunbeam's chief constituent. Light is of the highest importance to the health and well-being of animals, as may be inferred from the fact that animal life ceases in situations from which light is totally excluded. The case of the Proteus anguinus is exceptional, and therefore deserves some notice. This extraordinary little creature is found in some of the gloomy caverns of Illyria, into which the magic sunbeam never penetrates. At first view, says Sir Humphrey Davy, you may suppose this animal to be a lizard, but it has the motions of a fish. Its head and the lower part of its body and its tail bear a strong resemblance to those of the eel, but it has no fins, and its curious bronchial organs are not like the gills of fishes. They form a singular vascular structure, almost like a crest, round the throat, which may be removed without occasioning the death of the animal, who is likewise furnished with lungs. With this double apparatus for supplying air to the blood, it can live either below or above the surface of the water. Its 4 feet resemble hands, but they have only 3 claws or fingers, and are too feeble to be of use in grasping or supporting the weight of the animal. The hinder feet have only 2 claws or toes, which in the larger specimens are found so imperfect as to be almost obliterated. It has small points in place of eyes, as if to preserve the analogy of nature. It is of a fleshy whiteness and transparency in its natural state, but when exposed to light, its skin gradually becomes darker, and at last assumes an olive tint. Its nasal organs appear large, and it is abundantly furnished with teeth, from which it may be concluded that it is an animal of prey, yet in its confined state it has never been known to eat, though it has been kept alive for many years by occasionally changing the water in which it was placed. This strange creature, whose life is passed in total darkness, has long been a puzzle to philosophers, as all the facts revealed by science go to prove that light is indispensable to organization. The dependence of animal life upon light is beautifully exhibited in the ocean. Water is not absolutely translucent, and it has been calculated that light must lose all its influence at the depth of a very few hundred feet into the ocean, even under the tropics. Now it has been satisfactorily proved by an extensive series of dredging experiments that life diminishes as we descend into the ocean, and that beyond the depth of 300 fathoms it ceases altogether. But this is not all, for besides being much more numerous, the shells of the different mollusca are much more brightly coloured in the upper regions of the ocean than in the lower. In fact, a regular gradation of tints may be traced as the cells grow deeper in hue as they approach the light. Man himself is highly susceptible to the influence of light, and pines and sickens in darkness. Those persons who dwell in dark streets and alleys are far more subject to disease than those who reside in open places. Again, those who take no heed of the old proverb about going early to bed seldom find themselves healthy, and though they may be wealthy, they cannot be deemed wise. Light is absolutely necessary to vegetable life, for under its influence the plant separates carbon from the air and secretes it within its tissues. Everyone must have observed how plants grow towards the light, especially when confined in a room, how blanched and sickly they become in dark situations, and how speedily they recover when exposed to full sunlight. When a potato germinates in a dark cellar, it puts forth long pallid shoots in quest of a stray sunbeam, but let it be exposed to the light for a few days, and these shoots will become dark and green. Flowers are more sensitive to the influence of light than leaves. Indeed, almost every flower has a particular degree of light requisite for its full expansion. So regular are the periods of opening and shutting with some flowers, that they enable us to tell the hour of the day with tolerable accuracy. The great naturalist Linnaeus made a list of no less than 13 flowers that open and shut at different hours, and designated them by the fanciful title of Flora's clock. Having said enough to prove that there exists a mysterious bond of union between organization and light, let us now examine some of the effects of heat. The present condition of our earth is directly dependent upon the amount of heat we receive from the sun. If it were possible to move this planet nearer that orb, the quantity of heat would be much increased, and all the present races of plants and animals must perish. The same result would happen were the two bodies to be separated by a greater distance, owing to a deficiency of the genial influence. In the former case, the world would be much too hot to hold us, and in the latter, we should be regularly frozen out. The rays that are emitted from the sun are partly absorbed by the atmosphere, which acts as a screen, and shields the earth's inhabitants from the full and perhaps destructive influence of the sun's heat. The quantity of heat received by us in 1 year is prodigious, for it has been calculated that it would suffice to melt a shell of ice 46 feet thick and covering every part of the globe. The heat rays striking the earth become dispersed in a variety of ways. Some are reflected, others are absorbed. Some of the rays warm the earth, and then warm the overlying air, and expanding it, rise with it to the upper regions of the atmosphere. But by far the greater number of heat rays penetrate the earth, and descend to a considerable depth. In winter this stored up heat partly returns to the surface, and ultimately becomes dissipated into the air, and from the air into infinite space. Heat, like light, is absorbed in different degrees by different substances. The color and condition of surface seems to exert a great influence on its absorption. Thus a black body absorbs more heat than a white one, and a rough surface more than a smooth one. Every tree, says Mr. Hunt, spreading its green leaves to the sunshine, or exposing its brown branches to the air, every flower which lends its beauty to the joyous earth, possesses different absorbing and radiating powers. The chalice-like cup of the pure white lily floating on the lake, the variegated tulip, the brilliant anemone, the delicate rose, and the intensely colored peony or dahlia have each powers peculiar to themselves for drinking in the warming life stream of the sun, and for radiating it back again to the thirsting atmosphere. It is impossible to enumerate the wonderful offices performed by heat in the economy of nature. By the influence of heat, water is vaporized and raised into the air, thence to be precipitated in refreshing showers. The atmospheric currents are caused by heat. The trade wind that blows from the same quarter throughout the year, the periodical monsoon, the gentle breeze, the boisterous gale, and the devastating hurricane are alike manifestations of the activity of this mighty principle. Let us now glance at that mysterious element of the sunbeam which cannot be detected by the senses. To modern science is entirely due the knowledge we have gained of the chemical powers of the sunbeam. The old alchemists, indeed, were acquainted with the isolated fact that a white substance called hornsilver was blackened by exposure to the sun's rays, but it never struck them to investigate the cause of this curious phenomenon. It was reserved for a philosopher of modern times to prove that no substance can be exposed to the sun's rays without undergoing a chemical change. The blackening of hornsilver is but a single instance of a vast number of effects produced by that mysterious agent which is associated with light and heat in the sunbeam. All bodies are influenced by actinism, and undergo a chemical or molecular disturbance. The rock and the mountain, as well as the animal and the plant, are destructively acted upon during the hours of sunshine, and would soon perish under the delicate touch of the actinic rays, were it not for the counteracting influence of darkness. At night, the chemical disturbances are undone, and inorganic bodies as well as organized beings may be said to sleep. The influence of actinism upon germination is very remarkable, as seeds will not germinate in light from which this principle is separated. But after the leaves are formed, a larger amount of light than of actinism is necessary to enable the plant to separate carbon from the atmosphere and form wood. Again, the flowering and fruiting of a plant is more closely connected with the heat of the sunbeam than with its light or actinism. Nature has amply provided for the varying wants of plants. In the spring we may detect an excess of actinism in the solar rays, in the summer an excess of light, and in the autumn an excess of heat. We have said that all bodies undergo a chemical disturbance when exposed to the solar rays, but it must not be supposed that this disturbance always manifests itself in a blackening, as in the case of horn silver. If a polished plate of metal, of glass, of marble, or even a polished surface of wood be in part exposed to the influence of sunshine, it will, when breathed upon, exhibit the fact that a disturbance of some kind has taken place upon the portions illuminated, whereas no change can be detected upon the parts kept in the dark. But if we expose a chemically prepared tablet to the sunbeams in a similar manner, we may by a certain process render the effect produced on its surface permanent, and thus, as it were, fix a shadow. The beautiful art of photography or light drawing is based upon this marvellous fact. Everybody is familiar with the grand results of this art. Everybody has seen those wondrous pictures which neither pencil, brush, nor hand has touched, but which have been delicately traced by the magic sunbeam. We have ceased to look upon these pictures with astonishment, just as we have ceased to wonder at the locomotive, the electric telegraph, and the steamship. But in times gone by, had any one asserted that he could compel the sunbeams to paint a portrait, he would in all probability have been burned as a wizard. Indeed, not many years ago, a gentleman was thought to be disordered in his intellect because he deemed it possible to fix the fleeting pictures seen in the camera obscura. We cannot enter further into the magic of the sunbeam without leading our readers into the mystic regions of mathematics. We have already said that the subject is an inexhaustible one, and we are more convinced of this than ever when we find what a comparatively small number of facts relating to the wonderful band of forces called the sunbeam we have been able to set before the reader. But though so much is known about the sunbeam, how much still remains obscure. It is only lately that the existence of the mighty principle of actinism has been revealed, and who can tell what forces may still be hidden in the beam, what unknown powers may yet be brought to light by our laborious truth-seekers. End of Chapter 7. Chapter 8 of the Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. 2 eyes are better than 1. Mine eyes are made the fools of the other senses. Macbeth. The old proverb which heads this chapter is suggestive of many wonderful truths connected with vision. Science has demonstrated that 2 eyes are better than 1 for many reasons. We require 2 eyes to estimate distances, and to obtain a true idea of the roundness, relief, and solidity of natural objects. Those ugly one-eyed fellows who helped Vulcan to forge the thunderbolts must have been clumsy workmen, in spite of what the ancient writers say to the contrary. Before we consider the use of 2 eyes, let us examine the structure of a single organ. The eye has often been compared with the camera obscura, that dark box in which an image is formed of external objects, by means of an arrangement of glass lenses. The eye is, indeed, a dark chamber furnished with lenses, but here the likeness ceases, as its marvellous arrangements are infinitely more beautiful than those of any optical instrument devised by the ingenuity of man. The human eyeball is a globular mass, somewhat flattened in front and about the size of a walnut. The white part surrounding the centre is called the sclerotic coat, deriving its name from a Greek word expressive of hardness. This white coat is continued round the back of the eyeball, and forms a sort of strong bag for containing the other parts of the eye. As it is perfectly opaque, it is not continued over the front of the eye, but joins the beautiful transparent membrane called the cornea, or horny coat, which bulges forward a little, and forms that wonderful bow window through which the rays of light pass to the brain. Within or behind the cornea may be perceived the iris, a sort of coloured fringe which assumes different hues in different eyes, being dark brown, blue, hazel, or grey, and in exceptional cases red. When we speak of blue eyes or hazel eyes, we refer to the colour of this remarkable fringe or curtain. In the centre of the eye, surrounded by the iris, is a dark circular space of variable dimensions, called the pupil, which is in fact the opening through which the light passes into the dark chamber of the eye. The internal structure of this wonderful organ is very complicated. The hard white membrane is lined by a coat called the choroid, which is covered on the inside with a perfectly black pigment, and this again with a delicate network of nerves called the retina. The cavity surrounded by these coats is filled by three substances called humours. Behind the cornea or bow window is the aqueous humour, a perfectly limpid liquid resembling water. The second in situation is the crystalline humour, which is a little capsule of transparent membrane, holding a small quantity of fluid. And the third, termed the vitreous humour, is a transparent jelly which fills the inner chamber of the eye, and contributes chiefly to preserve the globular figure of the organ. Each eye is placed in a basin-shaped cavity in the skull, called the orbit, and there are various muscles attached to different parts of the orbit, which by their contraction give a lateral or rolling motion to the eyeball, and thus assist in directing the sight towards particular objects. Eyelids, also moved by muscles, and fringed by the eyelashes, serve to guard the eyes from dust, and to screen them from the access of too intense a light. So much for the anatomy of the eye. Let us now consider its functions. As already observed, the eye may be compared to a camera obscura, for the rays of light from any object entering the pupil form an image on the retina, just as the picture is painted on the ground glass of the camera. The various humours of the eye form a wonderful compound lens, far excelling the achromatic lenses of the opticians. The seat of vision is generally supposed to be the retina, though some philosophers regard the choroid coat as the sensitive tablet upon which the impression is made. We may trace the phenomena of vision up to this point, but no further. We know that a distinct image is formed upon one or other of the delicate coats of the eye, but the manner in which the sensation is conveyed to the brain is an inscrutable mystery. It is the boast of science, says Herschel, to have been able to trace so far the refined contrivances of this most admirable organ, not its shame to find something still concealed from scrutiny. For however anatomists may differ on points of structure, or physiologists dispute on modes of action, there is that in what we do understand of the formation of the eye so similar and yet so infinitely superior to a product of human ingenuity, such thought, such care, such refinement, such advantage taken of the properties of natural agents used as mere instruments for accomplishing a given end, as force upon us a conviction of deliberate choice and premeditated design, more strongly, perhaps, than any single contrivance to be found, whether in art or nature, and renders its study an object of the greatest interest. The Cyclops had each a single eye stuck in the centre of the forehead, but we are provided with a pair of these matchless instruments. Each eye receives an impression of an object, nevertheless we do not see the object double. So long as each image falls exactly on the same part of each sensitive surface, the mind will perceive but one object, and the muscles which move the eyes act in such perfect unison that this result is constantly attained. If we look at a candle placed at a distance of about 10 feet, we see it distinctly as one object, because our eyes are so adjusted that the image of the candle is projected on similar parts of each retina. But if we now hold up a finger about 10 inches from the eyes and look steadily at it, the candle will be seen on both sides of the finger. The eyes are now adjusted to the finger, and the image of the candle no longer falls on the same parts of the two retinae. Again, if the eyes are directed to the light, the finger will be seen double, because the optic axes are now adjusted to perceive objects at a distance of 10 feet. Similar effects may be produced by pressing one eyeball with the finger so as to displace its optical axis, or by getting intoxicated, an experiment which we trust our readers will never perform. We make use of our two eyes as a pair of compasses to measure distances, for we involuntarily associate the idea of smallness with the convergence of the visual axis, and that of vastness with its divergence. We feel that an object is near or remote, small or large, by opening and shutting our magic compasses, the legs of which are imaginary lines passing through the eyeballs. A person suddenly deprived of one eye estimates the distance of objects with the greatest difficulty. But after some time, experience teaches the one eye to measure distance by the change of focus alone. Let the reader close one eye and try to snuff a candle. He will then see the import of the old proverb, "Two eyes are better than one." We have said that two eyes are required in order to form a true conception of solidity. This point we now proceed to consider. If the reader will look at any near object, a book placed on end, for instance, he will at once perceive that it is a real book and not a picture of one. He will see that it has a certain relief, that one portion of it is nearer to him than another, in a word, that it is solid. Now, by closing each eye in turn, the reader will find that one eye will see round one side of the object, and the other round the other side, two different impressions being obtained. Every solid object, therefore, is seen differently by the two eyes, and it has been found that the effect of solidity is produced by the combination of these different impressions in the mind. Two eyes are better than one, not merely because they give symmetry to the face, but because they act together in producing on the inner or mental eye a perfect and instantaneous impression of the form and position of objects. This important truth has been revealed by the beautiful and well-known instrument called the stereoscope, which, however, is much better known than understood. Some account of this magic instrument certainly merits a place among the fairy tales of science. The stereoscope, in its most popular form, is simply a small wooden box furnished with two lenses, like an opera glass. A double picture, say a photograph of a statue, is placed at the bottom of the box and viewed with both eyes by means of the lenses. The effect is truly marvellous, for the design immediately appears in relief. The picture becomes a piece of sculpture. This illusion is so perfect, and the means by which it is produced so simple, that we cannot wonder at the popularity which the stereoscope has so rapidly attained. The term stereoscope is derived from two words in the Greek language, the first signifying a solid body, and the latter vision. It may therefore be freely translated as that which shows every object in relief. Our readers will admit that the name is a good one, and perfectly descriptive of the powers of the instrument. Let us now consider how the wonderful illusions of the stereoscope are effected. We shall not require diagrams to make our meaning clear, since everyone must be familiar with the construction of the magic instrument. The two pieces of glass that are placed in the front of the stereoscope are wedge-shaped, that is to say, their outer edges are a little thicker than their inner edges. These glasses act like prisms, and by bending the rays of light that proceed from the double picture, they cause the two halves to combine, and appear as a single picture occupying a central position between the eyes. Two distinct images are thus formed in the eyes, but in consequence of the bending of the rays of light, they are projected upon similar parts of the two retinae, and seem to be produced by a single object. Whether the two impressions are made by the double picture or by a single solid, the same sensation is produced, as in either case the mind combines the two impressions into the idea of solidity. The stereoscope, therefore, enables us to give a true notion of the form and position of objects from two flat representations on paper or glass. In fact, we may see the objects quite as well as if they stood before us. Although the stereoscope was discovered some 20 years ago, it has only lately become popular. So long as mere drawings by hand were used in stereoscopic slides, only regular bodies, such as crystals and geometric solids, could be represented. But now, by the aid of photography, we may obtain pictures of any natural or artistic objects. When we look at a double photograph in the stereoscope, the picture to the right is seen by the right eye only, and that to the left by the left eye. The two pictures are taken from different points of view, and are exactly similar to the views we obtain of solid objects by alternately closing the right and left eyes. There is, therefore, no longer any doubt as to the use of two eyes, since by the aid of photography we may obtain pictures similar to those which the eyes receive, and these pictures combine to produce the effect of solidity. We are indebted to Professor Wheatstone for the discovery of the stereoscope, a discovery which Herschel has truly characterized as one of the most curious and beautiful for its simplicity in the entire range of experimental optics. The original form of the instrument has been considerably modified by Sir David Brewster, who may indeed be regarded as the inventor of the refracting or popular stereoscope. We will not attempt to describe the innumerable family groups, landscapes, portraits, and Alpine views that photography has furnished for the stereoscope. Our readers are doubtless familiar with them, as the stereoscope has become quite a fashionable instrument, and has taken the place of the album upon almost every drawing-room table. Two eyes are unquestionably better than one. Nevertheless, persons with but one eye are able to see distinctly. This fact does not refute what we have said about double vision. A person with one eye judges of the relief of an object from the distribution of light and shade, but his perceptions are much less vivid than those of a person with two eyes. It has, moreover, been remarked that a one-eyed person, when looking at a solid object, is constantly changing the position of the head from side to side, and by this means he obtains with one eye the same result that is obtained by two eyes with the head stationary. Our readers will now understand why they have two eyes instead of one, and will be able to expound the mysteries of that magic spyglass, the stereoscope. End of Chapter 8. Chapter 9 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. The Mermaid's Home. Oh, what an endless work have I in hand to count the sea's abundant progeny. Spenser. Fortunate youth! What would we not give for a glimpse of a live mermaid, especially if she happened to be as beautiful as the submarine lady portrayed by our artist? We do not wonder to see you peering over the rocks so earnestly, but we entreat you to be careful, lest you tumble into the water. The belle of the sea is prettily dressed in her robe of seaweed, and the starfish on her forehead is a most becoming ornament. But how would you look in the sea, with your clean blouse and collar all wet and limp, with your trousers shrunk up to your knees, and your boots full of water? Hold tight to the rock, then, inquisitive youth, for we fear you would look a pitiable object as a sea boy. Would the reader like to take a peep at the home of the mermaid? If so, let him follow us in imagination to the bottom of the sea. We cannot promise him a sight of the mermaid herself, but we can show him some of the inhabitants of the deep that are scarcely less wonderful. Candidly speaking, we do not believe in the existence of the fair lady with the fishy tail, but for the sake of our fairy tale we will assume that she does exist, but is so excessively shy that she makes a point of concealing herself at the approach of strangers. The mermaid's home is beneath the wave, but we must not suppose that it is situated at an unfathomable depth in the ocean. The lady is far too fond of life and light to reside in a region beyond the reach of the genial influence of the sunbeam. Depend upon it, she has selected some quiet bay guarded by impassable rocks for her habitation, a bay whose waters are not too deep nor yet too shallow. Here is just such a bay as a mermaid might choose as a safe abode. Look how snugly the rocks shut it in on either side. A sea nymph might pass her days here without fear of molestation. Let us walk to the end of yonder jutting rock. Now, if you wish to visit the mermaid's home, prepare for a dive. So, 1, 2, 3, and in you go, head foremost. We are now safe on land, not on dry land, be it understood, but on the floor of the sea, with a good many feet of water overhead. We have ceased to be human beings subject to death by drowning, and have become the heroes of a fairy tale whom the elements cannot harm. Looking around, we perceive a host of wonders. We are in a new world, whose plants and animals have no resemblance to those of the world we have just quitted. Dense forests of many-colored algae are outspread before us. Uncouth creatures crawl at our feet, and fairy-like forms flit around us. If we wish to obtain a correct impression of these submarine wonders, we must examine them separately in regular order. We will therefore confine our attention at present to the beautiful herbs that grow in the mermaid's garden, and the miniature trees of her parks and forests. This lovely group of algae, misnamed weeds, will afford us ample types of marine vegetation. One of these plants, the green laver or ulva, has broad leaves of a beautiful emerald green, as thin as the finest cambric, and strangely puckered and folded at their edges. The mermaid doubtless makes use of these delicate leaves in place of silk or muslin, unless indeed she eats them as a salad. Beside this flimsy plant we see a cluster of crimson leaves, Delicaria, some 5 or 6 inches long, and of a most graceful form. The mermaid must take some pains to cultivate this herb, as its gorgeous colouring renders it a striking feature in her garden. Here is a tuft of what seems to be fine grass, here a group of rosy leaves, and here a tiny tree of a beautiful purple hue. In this little parterre we may find all the colours of the rainbow, and a wonderful variety of forms. Some of the plants are cut into fringes, some are spread out like fans, and others are divided into as many segments as are the graceful ferns of our woods. None of the marine plants in this group bear flowers, but nature has given them such brilliant hues that this fact might easily have escaped our notice. Let us now glance at some of the mermaid subjects, assuming the invisible lady to be the queen of these submarine realms. Among the happy living things of the sea, the fishes occupy the foremost rank, but we cannot bestow much time upon them, as we have to examine many less familiar creatures. But here comes one little fish, a black goby, whose strongly marked peculiarities at once attract our attention. His body is of a pale brown colour, with drab clouds and patches of white specks. He looks a terrible fellow, in spite of his mild eyes, which are light blue, and closely resemble turquoises. Now he hides behind a broad frond of seaweed, but we can see his wicked face projecting from the covert. We will watch this gentleman closely, as we half suspect that there is some mischief brewing. Another fish now appears upon the scene, a gentle and an unsuspicious fish to judge from his expression, a fish who would not hurt a fly, unless he happened to be hungry. Now this simple-minded creature approaches the place where he with the turquoise eyes waits in ambush. Assassin-like, the blue-eyed monster darts from his hiding-place, seizes his victim by the tail, and swallows him alive. Just look at the cannibal now. His distended body has become almost black, and bears witness to the blackness of his crime. How can the mermaid tolerate such a subject in her dominions? As we stand on the sea floor, the fishes that dart through the pale green atmosphere of water seem to be birds. That shoal overhead looks very much like a flight of swallows, and these restless little fishes, who are perpetually quarrelling and chasing each other, remind us forcibly of sparrows. What grace and symmetry belong to the forms of these finny inhabitants of the deep, and what exquisite hues gleam from their resplendent coats of mail. See, here comes the emissaries from the court of Oberon. No, they are merely shrimps and prawns, though their transparency and lightness, their graceful gliding movements, and the long and slender wands they wave, entitle them to be considered the fairies of the sea. Those who are only familiar with these creatures in their boiled condition can form no adequate conception of their appearance during life. In the mermaid's garden, these fairy-like beings take the place of moths and butterflies. Look at this little fellow, who moves about by discharging jets of water from a small tube or siphon, a mode of progression not uncommon among marine organisms. He hovers over a clear patch of sand, as though about to settle, while, by means of his magic siphon, he blows the sand from under him until a slight hollow is formed. Now he settles, but it is quite evident that his siphon is still at work, for the sand issues from all sides of his globular body in a little cloud, and he gradually sinks till nothing can be seen of him save his straggling arms and curious eyes. The mermaid has many expert miners in her service, but none to excel this cunning little well-sinker, the cuttle. These submarine regions are thickly populated by wondrous beings so transparent that they can only be distinguished by the flashes of light that gleam from their surfaces. Their substance is gelatinous, and strange as it may appear, consists chiefly of sea-water. Let us now examine a few of these living bubbles with the superior powers of vision which we possess as heroes of a fairy tale. How can we doubt the existence of mermaids when we find animals assuming the forms of umbrellas, goblets, and bells? Look, here comes a living umbrella, moving through the water by opening and shutting itself. Now, reader, it flaps itself under your very nose, and you may inspect it narrowly. You will perceive that it is rather an uncommon sort of umbrella, as it has 4 sticks instead of 1, and is furnished with a number of tendril-like appendages. You will also see that it is neither made of silk nor gingham, but of a delicate transparent jelly. This living umbrella, the Pelagia, may be taken as a type of the numerous gelatinous parachutes, bells, vases, and cups that glide through the sea. But here is a little object which deserves a separate notice, for it bears no outward resemblance to the bell-shaped creatures, though closely related to them. It is not easy to distinguish the form of this living lump of jelly. Now you may see it, though, if you look closely, as the light just catches its surface. See, it is a little egg-shaped ball of crystal, marked with longitudinal bands of the prismatic colors. 2 long threads that look like spun glass may be seen depending from its exterior, and these threads, if examined attentively, will be found to be fringed with yet finer threads or tendrils. Now this creature, the Cydippe, vanishes, and we are left to wonder how so much beauty could be compressed into so small a compass. Many of these gelatinous little creatures, which have been learnedly named acalophi, are phosphorescent, and at night they cause the sea to assume the appearance of liquid fire. How beautiful must be the mermaid's home when illuminated by myriads of these living lamps! Suppose we now take a peep at some of the creatures that dwell in the crannies of these jagged rocks, and wander through these miniature forests. We shall find them to be quite as remarkable as the free-swimming inhabitants of these submarine regions. The members of the great crab family are very conspicuous objects. They scuttle about in all directions, and their little bony eyes squint at us from out of every cranny. There goes a monster belonging to the edible species. Take care of his formidable nippers, or perhaps you will have cause to repent your visit to the home of the mermaid. Now he passes edgewise through a narrow chink in the rocks, and so disappears. We are not sorry to be rid of such an ugly customer. Look at that funny little fellow sitting on that large stone. He is a crab with some points that suggest the notion of a lobster, fringed swimming plates on the last joint of the body, large foot jaws, and very long feelers. Now he jumps off the stone, and by flapping his tail, swims just enough to enable himself to reach the sandy bottom slantwise, instead of going straight down, like some of his clumsier brethren. He now crawls about the seafloor, evidently in search of something, and now he disappears beneath a loose stone. He does not want much space, for he is as flat and thin as if he had been trodden upon. The naturalist has brought to light some strange facts illustrative of the domestic economy of this little crab. He usually clings to the underside of some flat stone or ledge of rock, and takes in the food that is brought to his door. His long feelers are constantly groping about for provender, which he fishes in with his outer foot jaws. Each of these jaws is like a sickle, composed of 5 joints beset with parallel bristles. When the jaw is straightened, the bristles stand apart and let the water flow freely between them. When the joints are bent to a curve, the bristles overlap and form a net or hair spoon. This net is the more perfect because each bristle itself is feathered with 2 rows of hair. After a haul, the little fisherman picks what he likes to eat out of his net and casts again. He throws his net out with the claws extended, and the meshes consequently open, so that all rejected particles are washed away. Then he again makes for himself a spoon wherewith to pick up victuals. In addition to his nippers, this porcelain crab has 4 pairs of legs, but only 3 pairs are at first sight visible. The 4th is a very tiny pair, folded down in a groove beneath the edges of the shell. Each of these little legs has at the end a pair of fingers and a little brush of hairs. With the 2 brushes it scrubs and cleanses its whole body, and with the 2 pairs of fingers, each being more properly comparable to a finger and thumb, it picks off any dirt that cannot be removed by brushing. But who is that long-legged little gentleman with the crusty and prickly body? He is another member of the prolific crab family, the spider crab, and is perhaps one of the most valuable servants in the mermaid's employ. He fulfills the important duties of a scavenger, and takes care that no decaying vegetable or animal matter shall remain long enough to be prejudicial to the purity of the sea. Instead of carting away the offal, this extraordinary little fellow crams it into his stomach, and appears to think it peculiarly palatable. Look at those shells that are moving about so clumsily among the pebbles. They are the habitations of the soft-tailed crabs, who, being unprovided with defensive armour, are forced to seek shelter in the empty shells of different mollusca. There is a tolerably large specimen of these creatures inhabiting a whelk shell. Look how awkwardly his claws, legs, and feelers loll out of the mouth of the shell. You would almost think that such a strange bunch of limbs would be utterly useless to the imprisoned creature. Here comes another, dragging a still larger shell after him. So prepare to witness a battle, for these creatures are terribly pugnacious. Now they meet and begin to fight in earnest, tossing their legs and claws about in a most excited manner. Look how clumsily they tumble over each other, and you must confess that a more comical duel never took place either above or below the wave. But see, the larger crab appears to have got the worst of the fight, for he is scrambling off as fast as his legs can carry him. These humorous creatures, the hermit crabs, must afford the mermaid considerable amusement. Indeed, it is highly probable that they are the jesters of her court. So many strange forms meet our vision in these submarine realms that we are puzzled as to which we ought to select for examination. Look at these richly coloured and gracefully formed shells. Each has its peculiar tenant, about which many wonderful things might be related. The shells, though beautiful themselves, are not to be compared with some of their inhabitants. Look at that periwinkle, for instance, who is now devouring the tender shoots of that plant. You must own that his zebra stripes and netted markings are exceedingly ornamental. But the periwinkle is not nearly so attractive as some of the fleshy creatures that may be seen protruding from their shells, and which have the richest hues imaginable. Again, just glance at those sea slugs, the nudibranch mollusca. How can we describe their various forms and colours? Here is one of a bright lemon colour, with a beautiful plume of feathers springing from his back. Here another of a pearly white, wearing numerous club-like ornaments. And here a third of a dingy grey, but furnished with a pretty little bouquet of flowers. The reader will perhaps be surprised when we tell him that these plumes and clubs and flowers enable the sea slugs to breathe, yet such is the fact, for all these ornamental appendages perform the same functions as our lungs. Here is a curious creature, closely resembling those we have just examined in form and substance, but belonging to a totally different class of beings. It looks like a milk-white slug, but if we inspect it carefully, we shall find that it is provided with 5 rows of delicate sucking arms, by means of which it clings firmly to the surface of the rock. It also has a chocolate-coloured head, tipped with a ring of feathery gills of white and primrose. Those naturalists who have studied the habits of marine creatures inform us that this white slug will throw away its inside when irritated, the body remaining but an empty sac, yet in a month or so the creature will begin to eat as greedily as ever, a fresh set of digestive organs having grown in the interim. This is a holotheria. Our artist has furnished his mermaid with a couple of star-shaped ornaments, and here we may see plenty of similar stars in motion. Whether we regard their symmetrical forms or their brilliant hues, we must admit these living stars to be the most remarkable inhabitants of these realms of wonder. Even this dusky red one, the 5-finger star, possesses great beauty, although its flaming relatives throw it into the shade. You see, it has 5 broad rays, but you must not suppose that these rays fulfill the office of legs, for the creature's legs, if so we may call them, are thousands of tiny suckers, protruding through holes in its under surface. Another member of the starry family may be seen clinging to the smooth surface of yonder rock, a 12-rayed sun-star of the richest scarlet. Here is another, the bird's foot star, a pentagonal disk of scarlet and orange, and here again another, the brittle star, a little flower-like disk with 5 long prickly arms that move about in a graceful serpentine manner. The last named creature is extremely sensitive to insult, and were you to handle him too roughly, he would probably commit deliberate suicide by breaking himself into little bits. But how did that little hedgehog find his way hither? Examine him closely, and you will see that he is not an ordinary hedgehog. He is an echinus or sea urchin. He is certainly covered over with prickles, but these, instead of being a dark brown, are of a pretty violet colour. Again, his form is much more regular than that of his terrestrial namesake, and he has neither head nor legs. He is a distant relative of the living stars, though you would hardly think so, judging from his external appearance. Look at these stony tubes twisted so curiously into a tangled group. These are the habitations of some of the mermaid's subjects. See, from the mouth of one of these tubes a conical stopper of a bright scarlet color emerges, and now a row of feathery objects which slowly spread themselves out into an elegant scarlet plume. Now another little stopper makes its appearance, another and another, and now each tube is crowned with its lovely tuft of feathers. Presto! They have disappeared. Plumes and stoppers vanished like magic as a large fish passed over them. The name of these creatures is Serpulae. This rock is studded over with tiny conical shells, each of which contains a living creature, a balanus or acorn shell, quite as wonderful as the tube-inhabiting worm. If you make good use of your microscopic eye, you will see that each little shell opens at the tip, and that a delicate white feathery object is alternately protruded and withdrawn through the aperture. This tiny white feather is a veritable casting net, and every time it is spread out it catches some invisible particles of food. We have glanced at a few of the mermaid subjects. To count them all would be indeed an endless task. In another chapter we shall describe at length some of the marvelous flowers that bloom in these submarine regions. Would that we could introduce the reader to the mermaid herself, but we sadly fear that she will never figure in the fairy tales of science. We are rather inclined to think that she ceased to exist with the dragons and griffins of that marvelous age known as Once Upon a Time. But perhaps she does exist after all, and only keeps out of the way of the naturalist, for fear he should bestow upon her some hard Latin name. However this may be, it is quite certain that the naturalist has never caught a glimpse of this mysterious being, though he has discovered many objects in the sea quite as extraordinary. And now, reader, we will once more become air-breathers, and bid farewell to the mermaid's home. End of Chapter 9. Chapter 10 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. Animated flowers. Here, too, were living flowers, which like a bud compacted, their purple cups contracted, and now an open blossom spread, stretched like green anthers, many a seeking head. Southey. The flowers of the sea far surpass those of the land in splendid and gorgeous coloring. In the gardens of Nereus there are anemones of the richest crimson, purple, and orange, chrysanthemums beautifully striped and variegated, carnations whose petals are exquisitely cut and fringed, and dahlias so perfect in form that they could not fail to win the admiration of enthusiastic flower fanciers. But these flowers are not only beautiful. Nature has endowed them with wonderful powers. They fold and expand their petals at will. Some of them can move from place to place, and others are so peculiarly sensitive that the slightest touch will cause them to shrink into shapeless lumps of jelly. What are these extraordinary beings? Are they plants or animals? Or do they stand upon some debatable ground between the two great kingdoms of organic nature? In ancient times they were doubtless regarded as sea nymphs, metamorphosed into flowers, but we fear that this opinion would have little weight in the present age of science. Expound the riddle, good naturalist, and tell us all about these animated flowers. Well, to put an end to the reader's suspense, we will at once inform him that these magic flowers are true animals. Nor will this statement surprise him, since he has already seen what marvelous forms may be endowed with animal life. He has seen living plumes, living stars, and living umbrellas, all of which are quite as wonderful as these living flowers. The sea anemones are by far the most conspicuous of the wild flowers of the deep, and we will therefore give them the precedence in our examination. If we wander about the sea beach at low tide, we may find plenty of these creatures attached to the rocks and stones left bare by the receding waves. The commonest are those known as the smooth anemones, or Actinia mesembryanthemum, which seem, when out of the water, to be mere knobs of jelly. On touching them, you find that they are tough and leathery, though you would never have imagined so from their appearance. These little knobs are variously colored, but different shades of green and red are their prevailing hues. When the sea comes up and covers the anemones, they assume the most lovely shapes. Each lump of jelly expands into a beautiful flower, having somewhat the form of a chrysanthemum, but a far more brilliant color. When fully expanded, each flower displays a ring of turquoise beads, whose pure blue forms a beautiful contrast to the crimson, purple, and orange tints of the petals. These jeweled flowers are not to be compared with their aristocratic relations, the thick-horned anemones, or Bonotis crassicornis. Words can convey no idea of the beauty of these creatures. They are much larger than the last species, and some of them, when expanded, are 5 or 6 inches across. Their petals, which are very thick in proportion to their length, are delicately transparent, and prettily striped and ringed with various brilliant colors. These animated flowers have been well likened to quilled dahlias, but to complete the simile, we must suppose that the terrestrial flowers have petals of gelatin. The daisy anemone, or Actinia bellis, is another beautiful species. They may be found in abundance upon some coasts, in the tide pools and hollows. In the sunshine of a fair day they expand beautifully, and you may see them studding the face of the rock just beneath the surface of the water, from the size of a shilling to that of a crown piece. If you touch one of these sensitive daisies, its circular disc will at once begin to curl and pucker at its margin, and soon take the form of a cup. If further annoyed, the rim of this cup will contract more and more, until it closes. The diameter of the disc is nearly 4 times that of the body at the point from which it expands. The petals are very small, but numerous, and are arranged on the disc in about 6 rows. As for coloring, the daisy is not surpassed by any flower of the deep, for though its tints are less brilliant than those of the living chrysanthemums and dahlias, they are so beautifully blended into one another that they cause the little creature to appear quite as lovely as its flaring cousins. The upper surface of the disc is of a rich umber brown, merging into lavender color towards the edge, the petals brown, blotched and speckled with white, and the base white, passing into pink, then lilac, and becoming purple as it joins the disc. But of all the flowers that bloom in the sea, perhaps the plumose anemone, or Actinia dianthus, is the most magnificent. It is much taller than any of the creatures we have described, and excels them in delicacy of coloring, pure white, pearly gray, or faint rose, taking the place of scarlet, olive, or brown. It is, indeed, a creature of surpassing loveliness, and has justly been styled the maiden queen of the beautiful tribe. The sea anemones are terribly voracious, devouring everything that comes within their reach. We are not romancing, dear reader. These flowers of the sea have wonderful appetites, and are endowed with digestive powers that the human gourmand might well covet. If we examine the internal structure of these anomalous beings, we shall be able to account for their voracity. A sea anemone may be likened to a double bag, the outer bag forming the exterior of the animal, and the inner one its stomach, the intervening space being divided into numerous chambers, by vertical partitions, which pass in a radiating direction between the outer surface of the stomach and the general integument. The arms or tentacles of the anemone, which we have hitherto spoken of as petals, are hollow, and communicate with the internal chambers. These chambers are always filled with water, and by the contraction of the walls, water is forced into the hollow tentacles. The tentacles are also provided with small orifices at the extremity, that can be opened or closed by the animal. Water is taken in by these orifices so as to distend the radiating chambers and tentacles, and is ejected with considerable violence through the same apertures whenever the creature is alarmed. The tentacles are placed in rows round the mouth, which is usually circular or oval. Although the anemone is a mere membranous bag distended with sea water, it is endowed with powers that render it more than a match for many animals occupying a much higher position in the scale of being. No sooner does a small fish, a crab or a shelled mollusk come within reach of its tentacles than it is seized by them and drawn to the gaping mouth of the greedy flower, the tentacles closing upon it on all sides. After a while the tentacles again expand, and an empty crust or shell is ejected through the mouth, the nourishing contents having been mysteriously extracted in the stomach of the anemone. And now, abstemious reader, can you wonder at the voracity of these strange creatures? If you had a stomach of proportional capacity, a mouth equally extensive, and 100 arms constantly picking up dainties, depend upon it, you would be quite as voracious. The anemone attaches itself to the rock by means of a sucking base, but it seldom remains long in the same place. In travelling, it pushes forward one portion of the base, and, having fixed it firmly, draws the remaining portion after it. a mode of progression very similar to that adopted by the snail. There are many more wonderful things connected with the sea anemones which we cannot stop to consider, as we must now pass on to another kind of living flower. The madrepore, or Caryophylla smithii, is allied to the anemones, but differs from them in many important points. This beautiful little flower of the sea has a stony skeleton, consisting of a number of thin, chalky plates standing up edgewise and arranged in a radiating manner round a low centre. We have informed the reader that the interior of an anemone is divided into numerous chambers by perpendicular veils of membrane. If he now will imagine that every one of these membranes is turned into stone, he will understand the formation of the madrepore's skeleton and its relation to the soft investing flesh. Mr. Gosse, the naturalist, to whom we are indebted for many striking facts relating to the beautiful inhabitants of the sea, has given a charming description of the living madrepore in one of his pleasant books. Let it, he says, after being torn from the rock, recover its equanimity, then you will see a pellucid gelatinous flesh emerging from between the plates, and little exquisitely formed and coloured tentacles, with white clubbed tips fringing the sides of the cup-shaped cavity in the centre, across which stretches the oval disc, marked with a star of some rich and brilliant colour, surrounding the central mouth, a slit with white crenated lips, like the orifice of one of those elegant cowrie shells which we put upon our mantelpieces. The mouth is always more or less prominent, and can be protruded and expanded to an astonishing extent. The space surrounding the lips is commonly fawn colour, or rich chestnut brown; the star, or Van Dyck circle, rich red, pale vermilion, and sometimes the most brilliant emerald green, as brilliant as the gorget of a humming-bird. The madrepores are quite as greedy as their wandering friends the anemones, and the presence of food stimulates them to more active efforts and the display of greater intelligence than we should give them credit for. Mr. Gosse relates a very amusing anecdote about feeding a madrepore. He once put a minute spider, as large as a pin's head, into the water, pushing it down with a bit of grass to a coral, which was lying with partially exposed tentacles. The instant the insect touched the tip of the tentacle it adhered, and was drawn in with the surrounding tentacles between the plates, near their inward margin. Watching the animal with a lens, he saw the small mouth slowly open, and move over to that side, the lips gaping unsymmetrically, while at the same time, by a movement as imperceptible as that of the hour hand of a watch, the tiny prey was carried along between the plates toward the corner of the mouth. The latter, however, moved most, and at length reached the edges of the plates, gradually took in and closed upon the insect, after which it slowly returned to its usual place in the centre of the disc. After some quarter of an hour, Mr. Gosse caught a housefly, and taking hold of its wings with a pair of pliers, plunged it under the water. The tentacles held it at the first contact as before, and drew it down upon the mouth, which instantly began to gape in expectation. But the struggles of the fly's legs perhaps tickled the coral's tentacles in an unwonted manner, for they shrank away, and presently released the intended victim, which rose to the surface like a cork, only, however, to become the breakfast of an expectant daisy, which was much too wise to reject or let slip so dainty a prey. The poor coral evidently regretted the untoward necessity of letting it go, for his mouth kept gaping for some time after the escape. In A Naturalist's Remarks on the Devonshire Coast. The animated flowers of the tropical seas far surpass those that bloom upon our own shores. In the Red Sea, for instance, branching corals, madrepores, anemones of the most brilliant hues, flourish in such luxuriance as to form a submarine garden of unparalleled magnificence. "Where is the paradise of flowers," exclaims a German naturalist, "that can rival in variety and beauty these living wonders of the ocean?" And these gardens of Nereus, through the introduction of the aquarium, may be brought into our homes. The brilliant and sparkling hues of the marine creatures will prove equally attractive in the tiny vase and in the boundless ocean, the more so as we may be fettered to bricks and mortar, shut in our town prison, or hemmed round by stern duties which we cannot elude, so the deep sea may roar a bluff greeting, but we hear it not. Let us consider how one of these mimic oceans may be formed. We procure a tank of plate glass, and cover its slate bottom with a layer of sand from the sea beach, or even well-washed river sand. But perhaps the best of all materials for forming a bottom are broken granite and coarse shingle. Rock work must now be introduced, so as to provide shady nooks for those delicate creatures that shun the light, or are of a retiring disposition. We may fashion the rockwork into a rude arch, or 3 large pieces of stone may be built up in the form of a table or druidical cromlech. The aquarium, having been filled with sea water, is now ready for stocking with marine plants and animals. The plants render the water fit for the maintenance of animal life, while the animals check the too rapid increase of vegetation. Thus, the success of our aquarium will depend upon the proper balance of animal and vegetable life. We select the green and red weeds, as the brown and olive are apt to discolor the water. Sea plants have no roots, but adhere by minute discs to the surface of the rock. A piece of stone has accordingly to be knocked off with each plant, in order that it may be removed to our glass tank. Some days should be allowed to elapse before the animals are introduced, so that the plants may have time to impregnate the water with their minute spores. Among the finny inhabitants of the mermaid's home, the little mullets rank first, then the blennies and gobies, but many other kinds of fish may find a place in our mimic ocean. The common periwinkle is essential to the aquarium, as it fulfills the duties of a scavenger and carefully removes the green film that sometimes forms upon the glass. The starfishes, crabs, serpulae, and the prawns are favourites with aquarian naturalists, but the lovely sea anemones are the crowning glories of the glass tank. We must carefully remove all dead plants and animals from our aquarium. It is indispensable that there should be a free access of light, but we must not expose our tank to the full glare of the sun's rays, or the water will become heated and its delicate inhabitants will surely die. These tanks require constant attention, but their beauty will more than repay us for any amount of trouble. They have been beautifully described as flower gardens which never wither, fairy lakes of perpetual calm, which no storm blackens. End of chapter 10. Chapter 11 of the Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. Metamorphoses. There is a difference between a grub and a butterfly, yet your butterfly was a grub. Coriolanus. Once upon a time an aged butterfly, with wings all crumpled and torn, crawled up the stem of a willow and seated himself on the nearest leaf. "My last moments are drawing near," said he, "but I do not repine, for life has become a burden to me. My wings are useless, my joints stiff and rheumatic, and my antennae have long since lost their exquisite sensibility. It is quite evident that my flying days are over, but so much happiness has fallen to my share that I have no right to complain." The butterfly had scarcely finished this soliloquy when a large tiger moth alighted on a leaf close by. "Ah, my friend," exclaimed the moth, "I am truly glad to see you. I have not many hours to live, and I wish to make you my executor. Do not start, my friend. I am old and decrepit, and you shall see me meet death with becoming resignation." The butterfly smiled sadly, and declined the proffered executorship, explaining to the venerable tiger moth that he himself was about to die. Now, by one of those wonderful coincidences, peculiar to fairy tales, a dragonfly, a gnat, and 2 small flies, all bowed down by the weight of years, settled in the neighbourhood of the 2 Lepidoptera. The order Lepidoptera, or scaly wings, includes butterflies and moths. After much mutual condolence, the 6 insects began to quarrel about their respective adventures, each bragging that he had seen far more wonderful things than had any of his companions. The dragonfly became very much excited, and though very feeble, he clashed his mandibles together in a manner that filled the smaller insects with dismay. The butterfly, who was an insect of very superior turn of mind, put an end to this disagreeable scene. "My friends," he exclaimed in a solemn voice, "is it wise to waste the few short hours that remain to us in vain discussion? Would it not be more becoming in old insects like us to sit down quietly and relate our adventures without quarrelling? Depend upon it, nature has not formed us differently, and endowed us with distinct faculties, for a mere freak, but because we may be better fitted to enjoy the sweets of life in our separate spheres. Consider, my dear dragon, what pitiable objects you and I would be were we to exchange wings. How could you support your long body with my painted wings? And how could I work your gauzy pinions with my feeble muscles? Instead of boasting about your superior strength and prowess, you ought to accept your gifts with a humble thankfulness, as you must be aware that you are far inferior in point of intellect to the sober bee or the tiny ant. "Do not be too hard upon me, Mr. Butterfly," said the great insect. "I own myself in the wrong, and am quite willing to adopt any suggestion you may make with regard to the manner of passing our last hours." The two little flies, on hearing their dreaded enemy speak so rationally, instantly recovered their self-possession, and the gnat actually ventured within the reach of his formidable mandibles. "Well, then," said the butterfly, "let each relate his history in as few words as possible, describing the metamorphoses he has undergone, and the wonderful things that have fallen within the sphere of his observation." This proposition was received with unanimous approbation, and it was speedily determined that the butterfly should tell the first story. We will now lay before the reader a true report of the conversation that ensued, adding such explanatory remarks as may be necessary to make the speeches of the insects intelligible. "I am generally known as the cabbage butterfly," said the first speaker, "and although my wings are now in a very dilapidated condition, I think you must admit that the dark spots upon the white ground produce a very pretty effect. I need not tell you that I originally came from an egg, which my maternal parent, guided by an unerring instinct, had deposited upon a leaf capable of affording me proper and sufficient nourishment in my caterpillar state. And a beautiful little egg it was, shaped like a flask, marked with 15 ribs, converging towards the smaller end, and having a delicate yellow color. I was a very little fellow when I made my escape from the egg, but having a tremendous appetite, I grew rapidly, and soon became a handsome caterpillar. Nature had furnished me with 16 feet, and had dressed me in a coat of bluish gray, having a bright yellow line down the back and another on each side. I am fairly shocked when I think of my voracity, for I frequently devoured double my own weight of cabbage in 24 hours. At length, when I had attained my full size, I felt that I was about to undergo a wonderful metamorphosis. Accordingly, I stole away from the plant on which I had been feeding, and found a secluded corner where I could perform unmolested the tedious and painful operation of wriggling out of my skin. Having thrown off my gray coat, and with it my 16 legs, I became a chrysalis, a Greek term signifying golden, applied to pupae on account of the golden lustre which they sometimes exhibit. A mere mummy, in fact, having neither limbs, eyes, nor mouth. My second metamorphosis was even more extraordinary than this. I broke through the mummy cloth as a perfect insect. My wings were at first moist and shrunken, but in an hour or so they spread out to their full extent. I will not attempt to describe the rapture which I experienced in my first flight through the air. My former life seemed to be an ugly dream, and as I flew from flower to flower, sipping ambrosial sweets, I could hardly realize the fact that I had once been a crawling caterpillar with an insatiable craving for cabbage. The longest life must have an end, and you now see me patiently awaiting death, or some new metamorphosis of which my instinct gives me no warning. The reader will doubtless be astonished to hear that the butterfly exists in the caterpillar, and has been detected in it by expert anatomists. In order, says Swammerdam, to discover plainly that a butterfly is enclosed and hidden in the skin of a caterpillar, the following operation must be performed. One must kill a full-grown caterpillar, tie a thread to its body, and dip it for a minute or two into boiling water. The outer skin will, after this, easily separate, because the fluids between the two skins are by this means rarefied and dilated, and therefore they break and detach both the vessels and the fibres wherewith they were united together. By this means the outer skin of the caterpillar, being separated, may be easily drawn off from the butterfly which is contained and folded up in it. This done, it is clearly and distinctly seen that, within this skin of the caterpillar, a perfect and real butterfly was hidden, and therefore the skin of the caterpillar must be considered only as an outer garment, containing in its parts belonging to the nature of a butterfly, which have grown under its defence by slow degrees, in like manner as other sensitive bodies increase by accretion. But as these limbs of the butterfly which lie under the skin of a caterpillar cannot without great difficulty be discovered, unless by a person accustomed to such experiments, because they are then very soft, tender, and small, and are, moreover, complicated or folded together, and enclosed in some membranous covering, it is therefore necessary to defer the operation just now proposed until the several parts of the butterfly become somewhat more conspicuous than at first, and are more increased and swelled under the skin by the force of the intruded blood and aqueous humour. This is known to be the case when the caterpillar ceases to eat, and its skin on each side of the thorax, near under the head, is then observed to be more and more elevated by the increasing and swelling limbs, and shows the appearance of two pairs of prominent tubercles. Before this beautiful discovery was made, the wildest theories were propounded to explain insect metamorphoses. When the butterfly had finished his story, the tiger moth addressed his friends in the following manner. I fear that my history will afford you but little interest, as I have undergone a series of changes of precisely the same character as those which have just been described by our friend. In my youthful days, I was quite as voracious as the butterfly, but my favorite food was the nettle. My body was covered with long hairs of a dark brown color. This woolly coat was of immense service to me, for besides keeping me warm, it saved me many a bruise by breaking my fall when I tumbled off a leaf or branch. Before changing into a chrysalis, I spun for myself a snug little silken hammock, in which I might repose in peace until my final metamorphosis into a moth. There, I have finished my brief narrative, and am now longing to hear the dragonfly's story, as I suspect it will be very wonderful. My early days, said the dragonfly, were spent in the water. I was then furnished with 6 feet, but I did not use them for walking, so much as for capturing my prey. I moved through the water by means of a wonderful hydraulic engine, which nature had given me. With this engine I was able to eject a stream of water to the distance of several inches, and this jet propelled me through the water in consequence of its being resisted by the stationary mass of the fluid behind. I was the terror of all the inhabitants of the pond, for I was dreadfully rapacious, devouring every living thing that came within my reach. In surprising my prey, I approached it very stealthily, and pounced upon it suddenly. I was so artful that insects, and even small fishes, found it difficult to elude my attacks. My first metamorphosis was inconsiderable, as my appearance underwent very little alteration, and I still retained my 6 legs, and had the same carnivorous propensities as formerly. At length I felt that the term of my aquatic existence had expired, and I therefore crawled up the stem of a water plant into the air. Having selected a dry spot, I pushed my sharp claws into the soft stem, and awaited my final transformation. By the swelling of the upper part of my body, the outer skin was greatly distended, and was eventually rent asunder on the back of the head and shoulders. Through this opening I escaped as a perfect fly, leaving the empty slough fixed to the aquatic plant. Old age has now come upon me, and I require no further nourishment, but I must confess that I never lost my rapacious instincts. Instead of seeking an innocent nutriment in the pulp of fruits or the nectar of flowers, I hovered in the air only to pounce upon other insects and crush them with my powerful mandibles. I have exterminated innumerable gnats and flies in my days, and have even caused the death of several moths and butterflies. This confession so alarmed the gnat that he flew at once to another leaf, so as to be at a safe distance from the splendid blue monster, for whom he had hitherto entertained so little fear. "Do not run away," exclaimed the dragonfly in a very jocular tone. "I shall not eat you until I have heard your story, provided you sit still. But if you attempt to leave this tree, I shall be very much offended, and will not answer for the consequences." "Oh, sir," exclaimed the gnat, "how could you suppose that I should run away from you, the handsomest, the best, and the most magnanimous insect that ever breathed? I moved from the leaf upon which you are sitting, because I felt my own unworthiness so keenly, and feared that my presence might cause you some uneasiness. If you would like to hear the story of my life, I shall be most proud to relate it to you, and to the other illustrious insects that are here assembled. I was originally produced from a tiny egg, shaped like a bottle. My mother knew that her offspring would pass the greater portion of their time in water, and she therefore deposited her eggs upon the surface of a pond. Now, as each egg was heavy enough to sink if dropped into water, she glued some 300 of them together into the form of a boat, which floated so safely that the most violent agitation of the water could not sink it, and what was still more extraordinary, it never became filled with water, even though exposed to the heavy rains. When hatched, I took the form of a minute, whitish, semi-transparent grub. I usually swam near the surface of the water, with my head downwards and my tail in the air, for my breathing organs were situated in the tail, and not along the sides as in caterpillars. In course of time I underwent a semi-transformation, like that of our noble friend the dragon, and 10 days after I broke through the skin that covered me and winged my way through the air. The reader would probably like to hear how the gnat escapes from its envelope without wetting its wings. The most important and indeed indispensable part of the mechanism is the maintaining of its upright position while extricating itself from the skin. The envelope, as it is thrown off, forms a lifeboat, and supports the gnat until it gets its wings set at liberty and trimmed for flight. The body of the insect serves this little boat for a mast. When the naturalist, says Reaumur, observes how deep the prow of the tiny boat dips into the water, he becomes anxious for the fate of the little mariner, particularly if a breeze ripple the surface, for the least agitation of the air will waft it rapidly along, since its body performs the duty of a sail as well as of a mast, but it bears a much greater proportion to the little bark than the largest sail does to a ship. It appears in great danger of being upset, and once laid on its side all is over. I have sometimes seen the surface of the water covered with the bodies of gnats which have perished in this way, but for the most part all terminates favourably, and the danger is instantly over. When the gnat has extricated all but the tail, it stretches out its 2 forelegs, and then the middle pair, bending them down to feel for the water, upon which it is able to walk as upon dry land, the only aquatic faculty which it retains after having winged its way above the element where it spent the first stages of its existence. The larger of the 2 flies came forward as soon as the gnat had done speaking, and gracefully waving his antennae, addressed the assembled insects as follows. I am a water-fly, and like the last 2 speakers, I spent my youth at the bottom of a pond. Having a very soft body, which required some protection from the rapacity of fishes and carnivorous insects, I enclosed myself in a case formed of bits of straw and wood, pebbles, and tiny shells bound together by silken threads, which I spun from my mouth. While I remained in the grub state, this case afforded me sufficient protection, but as soon as I felt a change approaching which I knew would render me helpless and inactive, I thought it advisable to contrive additional security. I therefore wove a silken grating at the entrance of my little gallery. This grating was marvellously strong, for I crossed and recrossed the threads until a thickish circular plate of brown silk was formed, which became as hard as gum. Of course I left a number of openings in this plate for the purpose of breathing. In this case I reposed in peace until just before my final metamorphosis, when I gnawed my way through the grating with a pair of mandibles specially provided for that one object. I then swam to the surface and underwent my change into a perfect insect. It is my turn now, said the other fly, a tiny creature with a black body and yellow legs, and although I am so small, I think I may safely say that I have led a stranger life than any of you. I did not pass my time, when in my caterpillar state, in looking out for food, yet I lived on the fat of the land. I am the dreaded ichneumon fly, and the egg from which I was produced was deposited by my mother in the soft body of a cabbage caterpillar, the brother probably of our friend here with the ragged wings. My kind parents settled upon the caterpillar's back and pierced the skin in about 30 places, depositing an egg in each wound. When we were all hatched, we set to work devouring the fatty portions of the caterpillar, who continued to eat as usual, though his food did not afford him much nourishment. When full grown, we ate our way through the skin of the unfortunate cabbage feeder, and immediately spun for ourselves a number of little silken cocoons of a bright yellow color, in which to pass the winter. In one of these little cocoons I underwent my transformations, and when I escaped, I had the form which you now behold. Such, reader, is the subject of a conversation which took place, or might have taken place, on the leaves of the willow, between 6 of our commonest insects. The metamorphoses of insects surely deserves a place in the fairy tales of science, as they are far more wonderful, because true, than any of the metamorphoses that we read of in the fairy tales of Greece and Rome. End of chapter 11. Chapter 12 of The Fairy Tales of Science by John Cargill Brough. This LibriVox recording is in the public domain. Water Bewitched. Fire burn and cauldron bubble. Macbeth. The vapor that escapes from the spout of an ordinary tea kettle is a much more wonderful emanation than any of those flimsy spirits which the weird sisters summoned from their magic cauldron. Those deluded old ladies, who wasted so much time in collecting disgusting ingredients for their infernal broth, in dancing wildly around their cooking utensils, and in breaking in and training broomsticks, have happily disappeared from the face of this beautiful earth. As we cannot look into their magic cauldron, let us peep into the homely kettle. Science has revealed so many beautiful truths concerning boiling water that we deem it advisable to devote an entire chapter to their consideration. The reader must not think that we have chosen a trivial subject. It has been well said that there is no great and no small in nature, and that the force which shapes the world gives form to the dewdrop. To this remark we may add a similar one, namely, that some of the grandest phenomena in nature are represented on a small scale in a kettle of boiling water. Mary, bring the kettle! Heat by entering bodies expands them through a range which includes, as three successive stages, the forms of solid, liquid, and air or gas, becoming thus in nature the grand antagonist and modifier of that attraction which holds corporeal particles together, and which, if acting alone, would reduce the whole material universe to one solid, lifeless mass. The influence of heat on the dimensions of material substances affords a convenient method of estimating the relative quantity of heat which will produce a given effect. For since it appears that a certain increase of temperature will invariably be accompanied by a certain degree of expansion of bulk, it follows that, if we can estimate the degree of expansion in any given case, we may thence infer the amount of temperature. Upon this principle depends the utility of those philosophical instruments called thermometers, or heat measures. As we shall frequently have to refer to the indications of the thermometer, we will describe the construction of this beautiful little instrument. The mercurial thermometer consists essentially of a fine glass tube with a bulb at one extremity, and which, having been filled with hot mercury or quicksilver, introduced through the open extremity, has been hermetically sealed while full, so that no air can possibly enter. As the tube and mercury in it gradually cool, the enclosed fluid contracts and consequently sinks, leaving above it a vacant space or vacuum through which it may again expand on the application of heat. To such a tube it is necessary to add a scale, showing at what height the mercury will stand at any given temperature, for a tube of mercury without a scale would be just as useless as a balance without weights. Now, to form a scale that shall agree with other scales, we must find two fixed points, and then divide the intervening space into a given number of equal parts or degrees. These fixed points are the temperatures of melting snow or ice, called the freezing point, and of pure boiling water, called the boiling point. The first is found by plunging the instrument into melting ice, and then, after the temperature of the bath is attained, marking the position of the mercury upon the tube. It is now placed in a deep metallic vessel nearly filled with water, which is heated until rapid ebullition ensues, and in this manner the position of the boiling point is ascertained. Fahrenheit's scale being the standard generally adopted in England, it is usual to divide the space between the 2 points into 180 degrees, the freezing point being marked 32 degrees, and the boiling point 212 degrees. In the centigrade thermometer, which is used on the continent, the space is divided into 100 equal parts, the 2 points being marked respectively 0 degrees and 100 degrees. The reader will understand that a degree of heat is a mere arbitrary division, and that 212 degrees Fahrenheit and 100 degrees centigrade indicate the same temperature. We shall adopt the unphilosophical but convenient scale of Fahrenheit throughout this chapter. No indication is afforded by the thermometer of the absolute quantity of heat contained in any substance, but merely of the amount of free or sensible heat capable of producing a certain degree of expansion in a column of mercury. If a quantity of ice, at the temperature of 0 or 0 degrees, be placed in a warm room, it will immediately begin to melt, and a thermometer plunged into it will soon indicate 32 degrees, though at first the column of mercury stood at 0. But, strange to say, the mercury will remain stationary at the freezing point until the whole of the ice has passed into the liquid form. Thus we see that a large quantity of heat is absorbed by the ice in the act of thawing, so as to be no longer appreciable by the thermometer. Again, if an open vessel containing ice-cold water be placed upon a fire, the temperature of the liquid will rapidly rise to 212 degrees, but at this point it will remain stationary until the whole of the water is converted into steam. The heat thus lost or absorbed during liquefaction and vaporization is called hidden or latent heat, in contradistinction to the heat of temperature. But we must not forget our kettle. The stream of vapor now issuing from the spout reminds us of the Arabian fable of the genie who escaped from the fisherman's bottle in the form of a column of smoke. But the genie of the tea kettle is infinitely more powerful than the genie of the bottle, who was, moreover, a stupid, blustering fellow, quite unlike our faithful servant Steam. Let us see how our mighty genie may be evoked. In other words, let us ascertain the conditions under which vaporization takes place. Vapors, of which steam is the most familiar to us, are light, expansible, and generally invisible gases, resembling air completely in their mechanical properties while they exist, but subject to be condensed into liquids or solids by cold. Steam is perfectly invisible, but as soon as it comes into contact with the cold air, it is condensed into a white cloud, which consists of minute liquid particles. When converted into steam, water undergoes a great expansion, a cubic inch becoming under ordinary circumstances a cubic foot of steam, or, to be exact, 1 cubic inch of water expands, when sufficiently heated, into 1,694 cubic inches of steam. We have already shown that this change, like the liquefaction of solids, is effected by the addition of heat to the water. But a much larger quantity of heat enters into vapors than into liquids, into steam than into water. If over a steady fire a certain quantity of ice-cold water requires 1 hour to bring it to the boiling point, it will require a continuance of the same heat for 5 hours more to boil it off entirely. Yet liquids do not become hotter after they begin to boil, however long or with whatever violence the boiling is continued. This fact is of importance in domestic economy, particularly in cookery, and attention to it would save much fuel. Soups made to boil in a gentle way by the application of a moderate heat are just as hot as when they are made to boil on a strong fire with the greatest violence. Again, when water in a copper is once brought to the boiling point, the fire may be reduced, as having no further effect in raising its temperature. If a thermometer be plunged into the steam that fills the upper part of the kettle, it will indicate 212 degrees. The steam is thus found to be no hotter than the water itself. What then becomes of all the heat that passes into the kettle, since it is neither discovered in the water nor in the steam? It becomes latent, that is to say, it enters into the water and converts it into steam without raising its temperature. As much heat disappears in the vaporization of a single pint of water as would suffice to raise the temperature of 1,000 pints by 1 degree. But the reader will be able to form a more adequate conception of the latent heat of steam from the fact that 1 gallon of water converted into steam will, by condensation, raise 5 gallons and a half of ice-cold water to the boiling point. Could we see through the sides of the kettle, we would observe so many strange movements in the liquid that we might easily persuade ourselves that we were peering into some magic cauldron. By substituting a thin glass flask for the kettle, the whole process of boiling may be seen to perfection. On gradually heating water in such a vessel, we first observe the formation of tiny air bubbles, which dart through the liquid with marvellous rapidity. As the temperature increases, these beaded bubbles winking at the brim give place to much larger bubbles, which are formed at the bottom of the vessel, and which rise a little way in the liquid, and then contract and disappear in a most mysterious manner, producing a hissing or simmering sound. But as the heating goes on, these bubbles, which consist of steam, rise higher and higher in the liquid, till at last they reach the surface and escape, producing a bubbling agitation, or the phenomena of ebullition. It may now be remarked that steam itself is invisible, as the upper part of the flask appears quite empty, but when it escapes into the cold air, it is condensed into a white cloud of minute drops of water. It was first remarked by Gay-Lussac, an illustrious French chemist, that liquids are converted more easily into vapour when in contact with angular and uneven surfaces, than when the surfaces which they touch are smooth and polished. He also remarked that water boils at a temperature 2 degrees higher in glass than in metal, so that if into water in a glass flask which has ceased to boil a twisted piece of cold iron wire be dropped, the boiling is instantly resumed. Solid bodies having different temperatures will, if kept in contact, gradually change until they all acquire the same temperature. But this diffusion does not take place instantaneously, or there would be no such thing as difference of temperature. The rapidity with which heat is conducted varies in different substances. For example, if we place a silver spoon and a wooden one in boiling water, the handle of the former will become too hot to be held before that of the wooden one is sensibly warmed. Silver is, therefore, a good conductor, and wood a bad conductor of heat. Liquids conduct heat very slowly and imperfectly. If mercury be poured into a jar, and boiling water be poured over it, the metallic fluid will receive heat but slowly from the water. A thermometer, let down a few feet below the surface of a pond or of the sea, would, on being drawn up, indicate a lower temperature than that of the surface water, for the latter, heated by the rays of the sun, communicates little or no heat to the water below. Indeed, it may be questioned whether water has any conducting power. It may be reasonably inquired how it happens that water is made to boil so readily by the application of heat. A little consideration will show that the effect, in a great measure, depends on the manner in which the liquid is heated, by placing it above the source of heat. If we require boiling water, we must place the kettle on the fire, and not in the ash hole. When heat is applied to a vessel of water, in the ordinary way, the fluid particles near the bottom of the vessel, being heated first and expanding, become specifically lighter and ascend, colder particles occupy their place and ascend in their turn, and thus a current is established, the heated particles rising up through the centre and colder particles descending at the sides. This is evidently a very different process from conduction. In the case of a solid, the heat is conducted from particle to particle, but in liquids there can be no change of temperature without a displacement of particles. Each particle, as soon as it receives a fresh accession of heat, starts off with it and conveys it to a distance, displacing other and colder particles in its progress. This process has received the name of convection. The more a liquid is expanded by a given change of temperature, the greater will be the difference of specific gravity between the part which is heated and the rest of the mass, and the more rapid, therefore, will be the circulation from the change. Any tenacity or viscosity in the liquid will impede its motion, and when water is thickened with flour or other farinaceous substances, it parts with its acquired heat very slowly. Many a person has burned his mouth with hot porridge, and expressed his surprise at the slowness with which it cools, without being able to assign the philosophical reason of the phenomenon. The currents that exist in the ocean are produced by convection, and are quite as easily accounted for as the currents in the heated water of our tea kettle. The oceanic currents are of great constancy and regularity, but they are modified in their direction by the general distribution of land and water on the earth's surface. That part of the ocean which is immediately under the tropics, and between the eastern and western hemispheres, for example, becomes highly heated. The water being greatly expanded, flows off on either side towards the poles, acquiring a westerly direction as it passes south of the coast of Guinea, and striking the promontory of Cape St. Roque on the South American coast, is split into two streams. The smaller one continues southwards towards Cape Horn, while the larger current maintains a northwesterly course into the Gulf of Mexico, where it receives further accessions of heat, and is gradually changed in its direction. It now passes along the southern shores of North America, and finally emerges northward in the narrow channel between the peninsula of Florida and the Bahama Islands, where it assumes the name of the Gulf Stream. The temperature of this current is found to be 9 or 10 degrees higher than that of the neighbouring ocean. This current passes on, gradually widening and becoming less marked, till it is lost on the western shores of Europe. A less accurately defined undercurrent from the poles is constantly setting in towards the equator, to supply the place of the heated water which takes the course already described. Besides rendering important aid to the navigator, these oceanic currents assist in maintaining an equilibrium of temperature on the earth, moderating the severity of the polar frosts, and tempering the sultry heats of the tropics. Among the circumstances which materially affect the vaporization of liquids, one of the most important is atmospheric pressure. We have said that water boils at 212 degrees, but this statement requires some qualification, as the boiling point of water will vary according to the pressure of the atmosphere as indicated by the barometer. The aerial ocean which envelops this planet presses upon the surface of the liquid ocean with a force equal to nearly 15 pounds on every square inch. In other words, a column of air an inch square, extending from the level of the sea to the top of the atmosphere, weighs between 14 and 15 pounds. The elastic force of air is necessarily equal to its pressure. Let us try to make this point intelligible to the reader. If the mercury of a barometer stands at a height of about 30 inches in the open air, indicating a pressure of 15 pounds, it will stand at exactly the same height in a closed room from which all communication with the external air has been cut off. The lowest stratum of the atmosphere is pressed upon by the strata above it, and being highly elastic, it assumes the condition of a bent spring. The confined air of the room is therefore able to support 30 inches of mercury by the elasticity which it acquired before the doors and windows were closed. We shall now be able to understand the relation that subsists between the phenomenon of ebullition and atmospheric pressure. Water evaporates or is converted into steam at all temperatures, until the whole space above it is filled with watery vapor of a certain elasticity. This is a wise provision of nature, for if water obstinately retained its liquid form at all temperatures below 212 degrees, the moisture that descended to the earth in the form of rain would never be evaporated during the hottest summers. But there is a difference between evaporation at low temperatures and ebullition or boiling. Water must be heated until its vapor acquires an elasticity equal to that of the atmosphere before ebullition can take place. At 212 degrees, the elastic force of steam will support a column of mercury 30 inches high, and at this temperature the steam bubbles acquire the power of breaking through the surface of the heated water, provided the barometer stands at 30 inches. Were we to carry our kettle to the summit of a high mountain, we should find that the water would boil at a very low temperature, and never become hot enough to make a decent cup of tea. Thus, at the town of Potosi on the Andes, where the superincumbent pressure of air will only support some 18 inches of mercury, water boils at 188 degrees. Again, were we to carry our kettle to the bottom of a deep mine, we should have to heat the water to a point considerably higher than 212 degrees before it would boil, owing to the increased height of the column of air pressing upon its surface. We now turn to the examination of another interesting point connected with the boiling of water. The reader will doubtless imagine that the hotter a vessel is into which water is poured, the sooner the liquid will boil. This is far from being the case, as may be proved by pouring a small quantity of water into a silver basin heated to redness. Instead of flashing into steam, as might be expected, the water will gather itself into a globule and dance about on the hot surface as if bewitched. The liquid is in a state of incessant motion. Sometimes it elongates itself into an oval in one direction, then, drawing itself up, it stretches out in a cross direction, and these changes take place so rapidly that a star-shaped figure or rosette is often the result. While the drop is in this spheroidal condition, as it has been called, let the lamp which heats it be withdrawn. The basin gradually cools, and after a short time the drop loses its spheroidal form, spreads out on the metallic surface, and is instantly thrown into violent ebullition. This striking phenomenon is generally known as Leidenfrost's experiment. All volatilizable liquids under similar circumstances behave as water does. Liquid sulphurous acid, for instance, when poured into a red-hot silver or platinum crucible, retains its spheroidal state, its temperature never rising beyond its boiling point. Now, as the boiling point of this liquid is 18 degrees, and therefore much below the freezing point of water, we can actually freeze water in a red-hot crucible by pouring it into the sulphurous acid. The same thing occurs with a mixture of ether and solid carbonic acid when introduced into a red-hot metallic vessel. The mixture requires for its conversion into gas as much time as it would in the air, at the ordinary temperature. If we introduce into this mixture a small tube containing a little mercury, the liquid metal instantly congeals into a solid. Again, in the place of a metallic basin or crucible, water near its boiling point may be made use of to support a drop of ether. Instead of mixing with the hot water, the ether gathers itself up into a globule and rolls about upon the surface of the other liquid. Let us confine our attention to the original experiment, to the dancing drop in the red-hot basin. By a series of beautiful experiments, it has been satisfactorily proved that the spheroidal drop never touches the heated surface, but is separated from it by a considerable interval. To what, then, is this interval due? Let us quote the words of a clever writer to whom we are indebted for many of the facts contained in this chapter. At an early period of railway history, it was proposed by that original genius, George Stephenson, to substitute for ordinary steel springs, in the case of locomotives, springs of elastic steam. It was proposed to convey the steam into cylinders, in which pistons should move steam tight. These pistons, supported by the steam beneath them, were to bear the weight of the locomotive. Now what the great engineer proposed for the locomotive, the spheroidal drop effects for itself. It is borne upon a cushion of its own steam. The surface must be hot enough to generate steam of sufficient tension to lift the drop. The body which bears the drop must be of such a nature as to yield up readily a supply of heat, for the drop evaporates and becomes gradually smaller, and to make good the heat absorbed by the vapour, the substance on which the drop rests must yield heat freely. In other words, it must be a good conductor of heat. It is to the escape of steam in regular pulses from beneath the drop that the beautiful figures which it sometimes exhibits are to be referred. By using a very flat basin over which the spheroidal drop spreads itself widely, we render it difficult for the vapour to escape from the centre to the edges of the drop, and this resistance may be increased till the vapour finds it easier to break into bubbles through the middle of the drop than to escape laterally. All these facts are in perfect harmony with the explanation that it is the development and incessant removal of a steam spring at the lower surface of the drop which keeps the liquid from contact with the metal and shields it from the communication of heat by contact. Owing to this, indeed, the liquid in the spheroidal condition never reaches its boiling temperature. If you plunge a thermometer into a spheroid of water in a red-hot vessel, its temperature will be found to be several degrees under 212 degrees. When the lamp is withdrawn and the basin cools, the tension of the steam underneath the drop becomes gradually feebler. The spring loses its force, the drop sinks and finally comes in contact with the metal. Heat is then suddenly imparted to the liquid, which immediately bursts into ebullition. It is well known that we may introduce the hand, if moist, into melted lead, nay, into white-hot melted copper or iron, and move it slowly about in these liquids, not only without burning the hand, but without even feeling the intense heat of the melted metals. Whereas iron or copper at a heat far below redness instantly causes a blister or burn. This apparent anomaly is easily explained. The intense heat of the melted metal instantly vaporizes the moisture of the hand, and the experimentalist receives no injury, as his hand is protected by a thick glove of non-conducting steam. It is highly probable that the priests of old were acquainted with this fact, and made good use of it in the ordeal of fire. When a person was accused of some crime which could not be proved against him, he was subjected to the fiery ordeal. That is to say, he had to plunge his arm into molten lead or walk barefoot over red-hot ploughshares. If he passed through the ordeal scatheless, his innocence was held to be satisfactorily established. Now the reader need not be told that the safety of the suspected person did not depend on his freedom from guilt, but on the moisture of his arm or feet and the heat of the metal. The greatest criminal might walk over hot ploughshares, provided they were hot enough to give him sandals of vapour. Truly, the humble tea-kettle is a wonderful suggestive. We had almost forgotten that it forms the text of the present chapter. But just now the water boiled over, and reminded us that we had not touched upon those grand kettles of nature, the geysers, or intermittent boiling fountains of Iceland. The geysers, of which there are a considerable number, are springs of hot water holding a large quantity of silex or flint in solution, which issue from the beds of lava of which the wonderful volcanic island is chiefly composed. A jet of boiling water, accompanied with a great evolution of vapour, first appears, and is ejected to a considerable height. A dense volume of steam succeeds, and is thrown up with prodigious force, and a terrific noise, like that produced by the escape of vapour from the boiler of a steam engine. Nature's cauldron boils over. This operation sometimes lasts for more than an hour, and after an interval of repose of uncertain duration, the same phenomena are repeated. The Great Geyser is the most celebrated of these boiling fountains. Sir George Mackenzie, who was the first to describe it, states that its eruptions were preceded by a sound resembling the distant discharge of heavy ordnance, and the ground shook sensibly. The sound was rapidly repeated, when the water in the basin, after heaving several times, suddenly rose in a large column, accompanied by clouds of steam, to the height of 10 or 12 feet. The column then seemed to burst, and sinking down produced a wave, which caused the water to overflow the basin. A succession of 18 or 20 jets now took place, some of which rose from a height of from 50 to 90 feet. The last eruption was the most violent. This being over, the water suddenly disappeared from the basin, and sunk down a pipe in the centre to a depth of 10 feet, but in the course of a few hours the phenomena were repeated with increased energy. The basin of the Great Geyser is an irregular oval about 56 feet by 46, formed of a mound of flinty deposits about 7 feet high. The channel through which the water is ejected is about 16 feet in diameter at the opening, but it contracts to 10 feet lower down. Its depth is estimated at 60 feet. From experiments made by the Chevalier Bunsen in 1846, it appears that the geysers are irregular tubes fed with rain and snow water, and that their peculiar form favours the heating of the lower portions of the contained water, by the subterranean fires, to a degree far above the boiling point. The eruption of one of these geysers is explained by supposing that when the whole of the contained water is sufficiently heated to allow of ebullition towards the upper part of the tube, portion after portion of the highly heated water successively bursts into steam as the pressure is diminished by the removal of the upper portion of the aqueous column. That this is the true explanation of the phenomena is highly probable, since artificial geysers have been constructed of iron tubes, which, being filled with water and heated near the lower extremity by burning charcoal, eject little columns of boiling water, and mimic all the phenomena presented by the natural geysers. Let us now ring the bell, and tell Mary to take away the tea kettle, for there is no knowing what abstruse subjects it may suggest, as it sits on the hob, singing its peculiar version of Home, Sweet Home. The reader must admit that the title we have chosen for this chapter is the only term that would embrace all the wonderful facts we have related. The bubbles and currents of boiling water, the dancing and ever-changing globule, and the huge cauldrons of Iceland fall quite naturally under the indefinite heading of Water Bewitched. End of chapter 12.